So it's my privilege to try to wake you up from a really nice dinner and my tasting from yesterday, and I'm trying to do my best to do so. But I'll start slowly though. Don't worry about that. So first of all, thank you very much for having me invited over here to a really nice place. And so I'll give you an overview of some work of my and also the Hellcats and Solar Primadog teams on the subject of, well, solar wind and mostly the global solar wind structure and evolution. Okay, so I'll leave aspects which are related more to small-scale processes to other speakers. We had Rian Lockman yesterday. We have Berto Bruno and the others following, which will give you more details about what happens at smaller scales. So I'll be more fixed at, well, large-scale scenarios. I'll try to make links, convincing links about how you go from solar wind modeling at global scales into continuous real-time forecasting strategies, of course, for space-weather purposes, and how that fits the exploitation of the future missions such as Solar Orbiter and Parker Solar Probe that we'll have in the next few years flying all together. So you have already seen these plots yesterday, but I'll show them again anyway. So what we see here is, as you see, two different times of the characteristic times of the solar cycle, the minimum and the maximum. You do see, well, the image of the corona just for reference. But the important bit is that you have this polar plot of the velocity as measured by Ulysses as it flew from pole to pole during two different orbits. So the striking thing that everyone noticed at the time was that at solar minimum at least, you do have a solar wind which divides very clearly into two components, which were called at the time the fast solar wind, well, because it's fast, and the slow wind component, well, because it's slower. When you go from minimum to maximum, you do see all this mess around here, but you can get convinced more or less that this is somehow a combination, an intricate combination of these two types of flows. All right? There's a little more to these anyway, so there's all other things you can see out of that. You do see that the fast wind flows, you do see these fluctuations there, which look a bit different than those there. So you can also see that you have, well, wave perturbations getting propagated in these regions, and other kinds of things, more compressible and shocks and other sorts of phenomena going on right there. But yeah, if you care about the large-scale structuring of all of these, it's really, as I was saying, really easy to get convinced that that distribution is just, well, to a large extent, a reflection of the structure of the magnetic field at any given time of the cycle. But yeah, of course, everything is more complicated when you look at things in detail. So there's slow winds and fast winds. They have different speeds, of course. Slow winds range from 300-ish kilometers per second up to, say, 450 or so, and the fast winds sit just above. But yeah, well, slow winds are denser and cooler, at least at one astronomical unit, when we measure them. But they also show different proton temperatures, well, generally speaking, different heavy ion compositions, different halvenicity, but most of all, you will see that, well, variability of all these, or dispersion of all these values is much higher on the slow wind part than on the fast wind part. So, one of the, I want to make a highlight about also something which dates from a while back. So in the old days of Helios, people had measured, well, Helios was a spacecraft that got us as close as we went to the actual sun. And people did measure some detection of flows, wind flows, which were slower than the usual solar wind flows. That is, they were at about 200, 150 kilometers per second or so. Tricky bit is that those flows were measured at those distances of a few, well, 10, a few solar radii, but we couldn't find any correspondence of that far away from the sun, say 20. So people thought of many things. Maybe these were just transients, or maybe flows which disappeared by the interaction, for example, with the neighboring flows which are faster. That could be the case. But a little more recently, we started working at the same data once again, and just looking at the different drift speed or relative speeds of, say, the alpha particles and protons, for example. And we have been finding some interesting things, which is that, so here you just have distributions of these different velocities, alphas and protons, for winds at different velocities. So very fast winds there, normal slow winds there, and really slow winds up there. So the important bit there is that the signal of these function kind of changes from there to there. We don't know exactly why, but we think this kind of change there is very sensitive to the heating processes that are happening down there, and also to the flux tube geometry in the very bottom of the atmosphere. The plot on the other side is also a very well-known plot now, which shows you the ratio of two different heavy ions, oxygen 7 and 6, for example, but there's other ratios of importance. And the interesting bit is that people started realizing that these abundances, or relative abundances, were different for fast winds and slow winds. But then, as people continued investigating, these plots just got all covered up, at least in this region there. So it's not just a matter of fast and slow wind, but there's something more to it. So we started realizing that all of these, you could probably separate all these plots in different regions, which are related to the kind of regions in the corona that the solar wind comes from. Or at least, well, that is composition somehow by transfer processes in different regions of the corona. There's a few more things also. So recently as well, some people have looked at streamer blobs, and this specific picture here shows a set of streamer blobs, or density features actually, which are observed in a part of the corona where we were seeing the heliospheric current sheet, which was very warped, very tilted at the time, so we were seeing it almost from the side. And people detected a series of density perturbations, which had a very clear periodic fluctuation of on the order of 17 hours that people interpreted as flux probes, or these magnetic islands, generated right at the streamer and Grunwald hole boundaries, well, at the edge of the heliospheric current sheets. From then on, there's been some discussion about how does this actually get formed. And people have been suggesting that there are similarities between epic processes happening, well, at smaller scales usually. So you can maybe invoke some sort of self-similarity argument to say that this kind of island formation that you see in big simulations, for example, could apply to those scales as well. That's not true. But anyway, getting back to the basics, or to the first things first. When we started looking at solar wind speeds, people started, of course, trying to come up with laws, initially analytically, for determining or predicting the solar wind speeds at any point or time of the heliosphere. So the most obvious phenomenology that we came up with was that, well, solar wind has to be guided along magnetic flux tubes, which have a whole range of geometries up there in the corona, and so it was easy to equate everything that relates to mass flux, energy fluxes, and all of that to the cross-section of to the variation of the cross-section of the flux tubes they go through. And so from that on, people defined a single parameter, which is called just total flux to exclusion ratio, and thought that, well, wind speed, which is being anti-correlated to that function there. And then with practice, people started having to add some few other parameters to get this expression, this kind of expression right. So this sits in the class of scaling laws, which are semi-empirical laws, which have some physics in it, well, a lot of empirical physics as well. There's another one of this kind, which works sometimes well, which is called the Grunwald-Harrier wind speed relationships. So you just look at the sun, at the region of the sun facing towards you, you consider the total surface of Grunwald holes that you see at a given time, and you derive, or you're able to estimate some wind speed that you get at you. Yeah, exactly. So, but this kind of semi-empirical approach have got a lot of shortcomings, notably all the fitting that you have to go through, and the fact that they are only valid to specific positions, say the ecliptic, 1 AU, whatever you want, and they will only give you speed at a given height, and nothing else. So to go through, understand the physics, and really get some predictability of these, you have to go through some kind of modeling, and to first approach at least some MHD wind modeling. So I'm showing you here two different types of models. No, it's the same kind of models, but which model the global corona and solar wind in two different ways. Some of these models have are more academic in scope, in the sense that this one at the left side, for example, is initiated using a solar dynamo model which runs for a few solar cycles, which then gets coupled with a loop model. While the one on the right side comes from a very well-known model as well, but is initiated with magnetograms. Well, the differences are not very essential. Essentially, to do all of these, you have to do a lot of compromises in the kind of geometry, not geometry, but on the thermodynamics most that you put in. You want to consider proper heating, proper cooling, proper classical transport process, of course. But that's just what you need to get a model which is reasonably efficient, that will get you the whole geometry up there. So I'll take this model here just to illustrate my next point. So these figures here show you two meridians of the solutions of that model. I'm just plotting there a bunch of field lines, open field lines, at the minimum and at the maximum of activity. And these field lines are colored as a function of the asymptotic speed of the wind that they carry out there. So you do have these very clear minimum situation there and maximum there, which you plot which you can plot. You just take the velocities out there and plot in a time latitude diagram, and you get something of this kind. So these kind of models, typically polytropic, this kind, have been very good at predicting the positions or the transitions between slow and fast wind flows with time and latitude. They are just not good at giving you the actual contrasts between these flows and those flows because they are missing on the thermodynamics. And this kind of models also allowed us to see something very interesting as well. So this plot here just shows you the latitude here and the total expansion factor that I told you about for two different instance, minimum and maximum. And again, all these points are colored as a function of asymptotic wind speed. So if you just focus on solar minimum, you'll see this very clear ordering between fast wind and slow wind, which anti-correlate to this expansion factor, right? But there are situations when this goes completely off. For example, there at this maximum, you do have fast winds there, slow winds there, with the same or even higher expansion factors there than there. So it only works every once in a while. So going through some analysis of these, let us realize that, well, geometry still matters for all of this distribution, is still the dominant factor, but there's more, it's just that there's more parameters to that. There's the expansion, but not just one value of expansion, but the actual profile of expansion matters, that is, the height and the radial extent at which expansion occurs. But there's also something that has been overlooked for a long time, which is field line inclination, or simply. Field line inclination will tell you, will change the pressure gradient of the winds feel at a given time. And if you go through the equations, even of classics or in theory, you can see that these two terms can have, well, the same sort of amplitude. All right, so that's more or less about what we can do right now with quick and semi-empirical models and the kind of things that we have to improve on those. But there's still a lot of missing there. So in terms of theory and modeling, all of these, well, large-scale models at least, are missing to a great extent a much better description of wave generation dissipation higher than the corona, well, anywhere in the corona actually, and multi-fluid, hybrid or kinetic models, anything that you need to describe heavy ion composition. And all of that, well, it's still in its infancy, I would say. Recently, we've been making a push for taking as many diagnostics about synthetic imagery or derive in situ signatures of this wind up there in the corona to make these models, well, testable or somehow predictable, right? And now, this all comes together with the efforts that people are doing in the community to build up space weather models. So, as I'll put it here, there seems to be quite a big difference in the attitude or the strategy that people pull up to do these kind of efforts and these ones. But in the end, maybe there's a way of bringing these two ways of doing it together. And I'll try to convince you of that just afterwards. So, in this slide, I'm showing you, I'll be describing a kind of a setup or a pipeline, if you wish, that we're setting up in my lab, actually, with the help of a bunch of people. And the whole idea is that, the whole idea of the pipeline is to build a very modular setup with different steps. So the first one,
for the first one, you just take some sun or surface observations, magnetograms typically, of any sort. From there on, you just do some kind of reconstruction using your favorite method, well, conventionally PFSS, but it can be anything else. This is that's what picture shows. And then, what I'll do is that I'll trace a large sample of open field lines down from the surface up to a few, well, say 30 solar radii or so, and run a 1D solar wind model along each one of them. Okay? Then that allows me then to bundle up all the whole ensemble of field lines together to build a proper data cube or a spherical data cube of wind properties, velocity, density, temperature, whatever you need out of that. And eventually, if you need to, do couple all of these within the spherical models to the propagation up to 1 AU or to any described position. So the advantage of these in respect to conventional 3D imaging models is that, well, it's much lighter to run, it runs much faster, there's no comparison. Because they run faster, you can focus on you can improve a bit the thermodynamics of the wind model down there. So I told you to go 3D, you usually have to make very strong approximations of heat balance and all of that. Here, you can do it a little better, as you'll see. All right, so this is just what the typical solutions show for solar minimum and solar maximum. Field lines, there's nothing new about that. And then when you compose the whole solutions, you get these kind of solar wind distributions. Again, for solar minimum, a typical fast wind, slow wind kind of situation. So this is just a blow up of this region there, so exactly the same thing. And for solar maximum, you get, well, a much more complex or integrated situation, as you would expect, of course. Now, as I was telling you, the good thing about this model is that you go really from the surface up to a few tens of solar radii, meaning that you have a bit of the chromosphere, the transition region, the corona, which is heated, in this case, by a phenomenological function. There's no way around it. So this plot here just shows you a sample, well, a random sample of field lines from this model, plotted from the surface up to up here, and colored, as usual, as a function of the wind speeds, of the speeds of the winds that they carry, the terminal speeds. So you see, well, there's a whole zoology of field lines. I'm not going to go through all that, just that you tend to have fast solutions which get hotter far away from the sun, than slow wind solutions which tend to be a little cooler, although they take a much larger spread, of course. The interesting bit here, I think, is that, well, we have a density as well, which is very stratified around there and there. And there's one important bit that comes out of here. So if you look at the low corona only, you see all this mass of densities that superpose over the place, that in the high corona get very well ordered here at Yaku zone. So if you look at that, you see that there is a correlation, or actually an anti-correlation between density. So high density meaning slow wind flows, and low density high wind flows as we expect. So this seems perhaps trivial, but it's not. If you start off from PFSS, as people usually do, PFSS or low radial field, you'll never get to these, which is, well, the observational constraint actually. And that's because PFSS will not guarantee that your field lines in the high corona are in pressure balance. So you do need that. You do need a certain level of adjustment to the expansion ratios in the high corona as well, to get from the, not just having the right wind distributions, but also the right density distributions. Right. And as such, as we have, well, in principle, a decent solution for wind density, we can produce synthetic images quite light, for example, of the corona. And this is what you get for one solar rotation. So on this map, you do see a kind of a C2 field of view with the sun there. And what's happening there, you do see all these mild, starting again. See a mild variability all over the place, with things that look like polar plumes appearing and disappearing up there, but really what's happening there is just you're seeing a quasi-steady solution of the sun turning right in front of you, right? And of course you can compare these with proper chronograph images at any time that you want, here or there. And so systematically, in terms of SPUDGE, what we're trying to do is to get solutions of, well, wind speed, temperature, density, and of course magnetic field at a certain height, in this case at 21.5 solar radii, which is the height at which typically hemispheric models start off from, right? So you have this for maximum, they produce for minimum, of course. And so that's enough information for you to get into these kind of models, hemispheric, and get them started only from physical quantities without ever resorting to semi-empirical predictions. This is the kind of solutions you get. So there's wind, faster wind and slower wind there. And you can place yourself at positions of any spacecraft and compare the profiles that are measured and the ones that are simulated around here. And we are starting to get a more or less consistent agreement between them. So why do we do this? Well, because it's a lot of fun to do that, but also because this kind of approach is the approach that lets us have some testability in respect to what the solar wind model is doing out there. So you have to know that there's the solar wind acceleration, and then all the flows that get accelerated and formed up to this distance will be reprocessed, compressed, or whatever happens up there, forming rotating density structures, and all of that will show up in this time series, in this time sequence plots. So you have to take that all into account to do proper testing of your wind model from down there up to the position of your spacecraft, of course. Now, as there is density, once again, we can do syntactic white-light images of the corona. We can do synthetic J maps as well if you need. And if you really want to go crazy about it, you can take these background wind solutions and add in perturbations that simulate CMEs that can be eventually cataloged. That's something we have been doing for the Hellcats catalog, well, consistently for the duration of the steering mission, of course. Now it's something that should be working from here on for the future, of course. All right, this is just the same thing as well. Once again, there's no button. So, one of the things that are interesting in this kind of approach, modeling approach, is that, well, the model is fast, of course, but not just fast, it's very flexible, well, and robust in a way. So, I told you I tend to sample the whole solar sphere, atmospheric sphere, field lines, but you can, if you wish, just restrict yourself very easily to a specific region of the corona. So, for example, on these plots that I showed you, so these kind of maps that I showed you, for example, these plots, these simulations take something like 6 hours to be run on a few hundred computing nodes, which is not a computing cores, which is not really a lot. But really, if you want to go faster, you can restrict that just to the region of interest that you have, for example, the ecliptic. That will take you down to half an hour, 1 hour, or something like that. Okay, so from then on, we are trying to discuss strategies of how to use that to do proper solar wind forecasting, and things that are coming through as important are that we do need some early on magnetogram data, or maybe some adaptive, like adapt solutions, of course, forecasts. To do all of that, we do need some imagery of the west limb, white light, because it tells us something about the pressure balance of the different flows up there. That's useful to check out the quality for model, and then we'll just use these wind model and other propagation laws to get those solutions propagated into the direction that we need, of course. One important bit that we are thinking of is that if we ever get to build, to launch a mission that will have a chronograph, and in situ measurements as well at L5, we get an extra measuring point there, which can be used to flag the solutions, of course, and also gives us some extra days of for our forecasting window. Okay. But that's not just that. So I told you at the beginning that we were worried about how to deal with solar orbiter data and all of that. And so one of the things that are important for solar orbiter is that one of the things that are important for solar orbiter is that we want to determine at all instance the connection or the connectivity between the surface of the sun and the heliosphere. Not just for, and that's not just for post-event analysis, not just to look at the data and make sense out of it, but also to, well, you want to be able to point your telescopes, specifically the EUI instruments which can have very small fields of view. You want to point them to target regions which will have potentially an impact at the position of the spacecraft a few days later, at a position where it will be a few days later after the propagation of the perturbances, of the disturbances that it makes. So at the solar orbiter modeling and data analysis group, work group. We are trying to make an exercise of just trying to assess the uncertainty of what we can do for connectivity and all of that. And so these plots there, which are movies actually, just show you a test run made with old data, but with the future solar orbits, where it traces down from the spacecraft, well, magnetic field lines down to the surface. Okay, and we do that by taking different extreme approximations for the solar wind stage. So what comes out of that? Sorry if you cannot see the very well. See, for example, so just to show you better, so this green line on those two plots is the limb seen by solar orbiter, which is sitting at this position at the moon. Okay, so these two orange circles correspond to the size of the field of view of EUI at any given instant of the simulation. Okay, so what comes out of this is that this is pretty close to perihelion. So what comes out of that is that the spread between these and that solutions can sometimes be very big, and up to something like 30 or even 50 degrees in longitude, for example. Okay. So the whole technique consists of, well, setting up a small pipeline once again, from which you just shoot a model of operation first, say post-event or forecast analysis. That doesn't change much really. So you just have to pick a date or spacecraft position and trace down magnetic field lines. But to do that, don't forget that you need to take into account some sort of wind modeling. Wind modeling means wind speed, but also wind profile. So the time it takes for a given wind flow to accelerate from very low speed to very high speed, which can be something like 2 or 3 solar radii, but it can also be something like 20 solar radii. And that makes a huge difference in the propagation delays and hence on the azimuthal drift of the connectivity that you predict. So the modeling that I was talking about will enter into that part of this set, and it seems to be really a very important part of all of these. So to conclude, a bit speaking about solar wind, specifically solar wind at large scales, and we've been progressively convinced that the geometry of the magnetic field is really key, or probably a dominant factor in determining the speed and density distribution, again at large scale as well. Heating matters a little less, and there's different parts of that. There's a low coronal part of it, which has to do with expansion factors the usual way, and there's stuff that happens in the high coronal, which has to do more with the interaction of the different wind streams among themselves. Heliosphere, I should add that as well, heliosphere rotation and whatever happens in the heliospheres. Causes for heavy ion composition are still unclear, although they seem to be related with solar wind sources, and also the transport mechanisms that allow plasma to go from one, say, close field to the solar wind. So I'm talking about a new kind of modeling pipeline, which aims at simulating the solar wind at global scales, being fast, and being an alternative to semi-empirical approaches or full 3D MHD models. We are trying to set it up by using a forecast data simulation techniques, using typically adaptive maps, and going from single fluid, which I didn't really talk about, into multi-fluid or hybrid approaches for these multiple solutions. Now, in the view of solar orbiters and the Parker Solar Probe flying together in the next slide, we are feeling the need for, well, let's say smarter modeling in the sense that we need both very computationally heavy models, but also we need quick and robust models to do all we need to do to relate data from in situ to remote observation, of course. Remember as well that speed and density will be measured in principle by the Solometics instrument just in the acceleration region of the solar wind, which will be really a great opportunity to test all these theories out. And that the Parker Solar Probe will be flying really close to the wind, and will maybe be able to probe these slow and even the very slow solar wind, which is simply high road. And will maybe let us get a grasp on what happens in terms of turbulence and wave propagation before the heliosphere preprocesses all that dynamics. There's also other mission concepts around which can have an importance to all of these, such as the more space weather-oriented L5 missions, or other more solar wind-oriented missions such as Thor. All right, and I'll stop here, and thank you very much for your attention.
So, I like to start from this very old picture from Undaussenburg, 1972, where it shows this fast wind expanding in the ambient solar wind. You can see here the stream interface, fast wind, the rarefaction region, and the ambient solar wind. Now you can see on the other picture on the left side the variability of the parameters of these different regions, like the velocity, the alphanicity, which is computed in this case in terms of cross-helicity and residual energy. There's this one, and you can see how the alphanicity is much higher in this green region, which is the fast wind, and then goes down in this rarefaction region and very low in the ambient solar wind, the slow wind. Then you see the temperature, the variability of the temperature, magnetic field, density. You see the stream interface density increases a lot, and finally the plasma beta around 1. Now, when you move from this region to the next one, you see that the alphanicity changed very quickly. And in particular, I want to show you in this slide over here, in this figure. This is part of the fast stream. You can see how, when you move from this region to this one, the amplitude of the fluctuation is much smaller, but this happens very quickly. And also the anti-correlation between velocity and magnetic field decreases quickly. So there are large differences in nature, in the nature of the fluctuations when we go from the fast to the slow wind within a high velocity stream. And I will come back to this later on. If we want to map back our stream to a few solar radii, you see in this graph over here that the fast stream comes from regions which are at high heliomagnetic latitude, so far from the equatorial region, and the slow stream comes to regions which are much closer to the magnetic equator. This is a power spectrum of typical power spectrum of magnetic fluctuations in the solar wind, in the fast wind, I would say. This is typical of fast wind. In the slow wind, this range over here is much more difficult to find, but there are some evidences now that there is also a break point in the slow wind, but at a frequency which is not the one that you would predict from the radial dependency of this breakpoint from distance. Anyhow, you can see the three different ranges f to the -1, typical Kolmogorov range f to the -5/3, and then what is the so-called dissipation range, something like around f to the -3. If we, in a framework of Richardson cascade, we have that energy is injected in this range and then is transferred through via nonlinear interaction. This is the convective derivative in the Navier-Stokes equation. This has to be different from 0 if you want to have nonlinear interaction over here. So energy is transferred without dissipation along this inertial range, to be eventually dissipated over here in the kinetic range and heat the plasma. There are two breakpoints in this typical spectrum. The first breakpoint is this one and corresponds to the correlation length of your sample. But what about the second breakpoint? The second breakpoint should be something which indicates the Taylor scale in this process. However, there is a lot of literature about this. Many papers have been written in the past few years about the location of this high-frequency break. But there is no full agreement between all these results. The only thing about which we are more or less sure is that the breakpoint at high frequency should be at proton scales, like inertial length or Larmor radius or something close to that. In a study that we made in 2014, we found that the location of the high frequency break is well predicted by the weight number, but very well predicted by the weight number Kr, which is associated with the ion-cyclone resonance condition for parallel propagating alpha waves. Here you see the results. The red triangles are for the resonance condition, and green and blue are for the Larmor radius and inertial length. So you see the better correspondence for the resonance condition. However, this is unexpected because we know that turbulence proceeds via K-perp, not K-part. So why this break should correspond to this, to K-part? And this is a question mark. This has to be understood, and so the story about the location of the high frequency break is not over. Moving on, I show you a second feature of the spectral break, the spectrum within fast swing. Here we have three different streams, fast streams, and we have several spectra which correspond to different speed within each of them. So this one corresponds to the first one, and you see that when we move from the faster to the slower wave, not only the energy content in the inertial range decreases, but also the spectral slope in this short frequency range, which is a kind of transition range between the inertial and kinetic regime. So when you go from faster to slower wing, this spectral index will become flatter. This has been found in all the fast streams that we have analyzed, and these are just few examples. Now, there is a relationship, a power law, between the spectrum, the spectral index in this part of the spectrum, and the power which is associated to the inertial range. More power you have in the inertial range, steeper is this part of the spectrum. This is the distribution of the spectral index with respect to the power in the inertial range. And you can see this this state over here, which will tell you that the relationship between these two parameters is this one, and for a asymptotic behavior of this relation, you will find that the limiting value for Q is minus 4.4, plus or minus a big arrow. Okay? So this means that you are not supposed to find a spectral index larger than this in the fluctuation in the surrounding. The third spectral feature I want to talk about is related to this part of the spectrum, which is the kinetic regime. So this is one event that we found during an alignment between Wien and Themis, 1AU. And what you see is that no matter which velocity you are analyzing, you always have this part of the spectrum which is not very sensitive to fast or slow wave, whatever. This is above 1 Hz, more or less. Okay. So the question now is this general behavior of the interplanetary magnetic field spectrum, or just a fortuitous case that we found? So we look for more events. However, to do this kind of studies, you need very high sampling frequency for the magnetic field to study the magnetic regime. So you need data from the search coil magnetometer. And you also need data from the flux gate magnetometer for larger scales. Now, and you have to have these sampling along the velocity profile. So, but there were strong limitations due to the orbits of Themis and Pulsar, because they go in and out in the magnetosphere, but we want to be in the solar wind. So we were able to select, okay, only 4 co-rotating high velocity streams, 3 for Themis and 1 for cluster. This is the list of them. So this is, I will show you just one stream. This is one in May 2011. And this is the spectrum which corresponds to this interval over here. So you can see it's slow wind, so we have the nice, minus 5/3. Then we also reported the 3 wave numbers corresponding to resonance, Larmor radius, and inertial length. And this is the kinetic regime. Now we move to the next interval. Okay, you see not much is happening over here. We move to the other one, and then the other one. So as you see, there is a large variability over here, but there is more variability over here. Then if we put together all the fastest intervals in our 4 streams and all the slowest intervals, and we move from one to the other one, you can see that things are changing a lot in the inertial range, but not much at kinetic scales. Now, if we put all together, we have this situation right here. And if we consider that kinetic range is characterized by very slow variability, the spectrum is around minus 2.5, 2.7. And here we have a k to the minus 5/3 well established, and these 2 regimes have to be connected somehow. So we end up saying that there must be a sort of lower limit for the power spectrum density, a sort of background magnetic field, background spectrum. Now, if we take into account what we said before, the maximum slope, which is expected, the spectral rate more or less is around this frequency over here. The width of this region is less than 1 decade. We can draw this dashed line over here, which will tell you that the max will indicate the maximum power density that you would expect in fluctuations of the solar wind within fast streams. So the variability expected then is a sort of 10 to the second. Now, in order to get this data, this analysis more robust from the statistical point of view, we looked at 12 years of data. We selected just one wave number. We estimated the power associated to that scale within 12 years of data, and we reported this in this histogram, where we have the variability of this, the power associated to this within 12 years. So this is mainly in the slow wind. This is in the fast wind. There's a larger variability as expected in the slow wind. We can reproduce the distributions for slow and fast over here, and we can estimate the maximum variability that we would expect, taking into account the width, the top maximum of these distributions. If we do this, this is about 2 decades again. So this is a sort of confirmation of the results that we had with only those 4 streams. So the conclusions are over here, and I'd just like to highlight that the scenario that I showed allows to estimate the upper limit of the intensity of the superposed affine spectrum on this background spectrum, and this can be a reference point for modeling of solar wind fluctuations and dynamics of solar wind. Thank you.
Ladies and gentlemen, first of all, thank you for the organizers for inviting me. And I am from the Space Institute of Physics, University of Graz, Space Research Institute of the Academy of Sciences. I have also an affiliation in Hungary, and my collaborators are from Space Research Institute Graz. Here is the outline of my talk. I will talk about in situ observations of magnetic reconnection, and I will show you what are the typical in situ signatures of magnetic reconnection. I will demonstrate this using 2 observed cases in the Earth's turbulent minor sheath. What is the difference between remote sensing and in situ measurements? I guess you know this part of the story because the majority of you are solar physicists. So this is the standard flare model, remote observation, and we have plenty of remote signatures of reconnection. There were also flow signatures, plasma inflows and outflows were observed in the sun. So we are interested in the central part of the reconnection, which is, we know from in situ measurements, is of the order of 100 kilometers or less. Okay. Where the in situ measurements were realized. First of all, we had plenty of missions observing the Earth's magnetosphere. Then also in the solar wind, the reconnection in the solar wind was observed later. It was overlooked for some time. And the typical reconnection signatures in the solar wind are the decreased intensity of magnetic field and also the reconnection outflows and the rotational discontinuities at the border of outflows. In the Earth's magnetosphere, first of all, we have reconnection at large-scale boundaries like the Earth's magnetopoles and in the magnetotail current sheet, also in the cusp regions, and recently we have reconnection observations in the turbulent magnetosheaths. So the question is, if the reconnection observed at the large-scale boundaries is the same as reconnection in turbulence. The point is that it's very easy to see the large-scale boundaries, for example, moving magnetopoles from the data. But the reconnecting current sheets in turbulence, it is not so easy to observe, to identify. This is the case of, so here is the bow shock, the magnetopoles, and this is simulation by Karim Abadi showing that behind the quasi-parallel bow shock, the quasi-parallel bow shock is when the bow shock normal, the angle between the bow shock normal and the interplanetary magnetic field is between 0 and 45 degrees. In this case, the magnetosheath is much more turbulent than behind a quasi-perpendicular shock. Okay, so we are going to this region. Why? Because we want to use MMS measurements with very, very high resolution plasma data. And just now, if we talk about turbulence, we have data from this region. Simulations show really that in terms of the plasma velocity and the magnetic field, the quasi-parallel magnetosheath is really turbulent. We have vortex-like structures, then we have these high-speed streams which are even reaching the magnetopause. The magnetopause is here, the bore shock should be somewhere here. You don't see even the bore shock very well. Okay. We made the preliminary analysis in Graz on the basis of MMS data, looking into the jets. And we observed that the jets have a relative motion to the background plasma. And this motion is supermagnetosonic in the reference frame of the Earth, but submagnetosonic in the reference frame of the plasma. And therefore, there are no slow shocks around, okay? No shocks. And here is the observation, again, the simulations showing the current density structures. The message here is that turbulence generates small-scale coherent structures. And those small-scale coherent structures are currents or current sheets. And the dissipation, even if we compare MHD or peak simulations, the dissipation usually happens at those current sheets. Okay, there is plenty of literature about this, and also some observations. I am not going into details. So how to observe local current sheets which are not large-scale boundaries in turbulence? First of all, we can look into the local enhancements of magnetic fluctuations relative to a fluctuation background. This is the so-called partial variance of increments. We have local fluctuations relative to a larger scale background. And we can also calculate the local magnetic rotation angle. So if we have a current sheet, which is a discontinuity, these two parameters should observe locally the current sheet in turbulence. So this is the simulation. And this PVR parameter, you see, has very intermittent peaks. And over the threshold, there are the strongest fluctuations. So if we look into strongest fluctuation, these are cluster data, and calculate the same PVI parameter, we see similar peaks. And if we look into one peak, then here is the magnetic field, the PVI, the rotational angle of the magnetic field. You see that there is a component of the magnetic field which is changing sign. So it's almost anti-parallel in terms of the magnetic rotation angle. And the PVI is showing a peak. So this is a local observation of current. Okay. So conclusions one. Using PVI magnetic rotations, and then we can calculate the local current densities. These quantities enable us to observe local current sheets, perhaps reconnection current sheets in turbulence. The second is that I was not showing in detail, but the statistics of strongest current sheets resembles the statistics in simulations. Okay, now about MMS mission. We have 4 spacecraft in tetrahedron configuration. The separation distance between the spacecraft is of the order of 10 kilometers. Tetrahedron is important because using tetrahedron we can calculate gradients. For example, we can estimate the current density locally. Then we have magnetic field observations with 1 kilohertz resolution, electric field 8 kilohertz resolution. And this is the main point here. We have ion moments and VDFs, and electron moments and VDFs with this unprecedented 150 millisecond and 30 millisecond resolutions respectively. From the previous missions, the best resolution was 3/4 second. 3/4 second, okay. Now, here's an example of a reconnection event. We published it in GRL last year. And I'm not going into the details here because I want to go the details, demonstrating the other reconnection event, which is much better documented. Okay, but what I want to say, here is the large change in the total magnetic field, and if we look into the ion and electron speeds, you can see that the ion speed is varying smoothly, but the electron speeds has these very large peaks, and also the electric field, and also we have locally enhanced current densities. And from this, the difference between ion and electron speed, we can say that there is ion-electron differential motion, so we have currents, okay. And then we have large changes in the magnetic rotation angle, the PVI parameter again showing peaks, and so on and so on. Usually we need to calculate, we need to transform the variables to the reconnection element system. Element system means that we suppose that the reconnection can be understood as quasi-2D structure. Why it is important? Because we like simplicity. In turbulence, probably reconnection is three-dimensional. But let's try, because of simplicity concept, try to find two-dimensional reconnection. In this coordinate system, the LMN is, the L coordinate is the reconnection outflow, the M is the normal to the current sheet or the inflow, and the M direction is the out of plane direction in which very strange things are expected to happen, at least in this 2D model. So the third direction is important because if we calculate the generalized Ohm's law, of course this is the whole term, the divergence of the electron pressure tensor, the inertia term, these quantities should be enhanced when we are reaching smaller scales, okay? Also, we are calculating the anisotropy, agilotropy parameter, which is calculated from the electron pressure tensor. I will tell you why, okay? So, we transform all the variables to the field-aligned coordinate system. The one coordinate is along the magnetic field, another is along the E cross B convectional direction, and the third direction is the E cross B direction, the third perpendicular direction. The story is that when we expect the reconnection to occur here, we have this, for example, here is the electron pressure tensor divergence. It's enhanced. We have the agilotropy parameter also enhanced. And when it happens, we have, this is the ion VDF, perpendicular, one perpendicular, two direction. From this VDF we can see plasma mixing because reconnection is mixing plasmas, okay? Good. Let's, it's not important. Let's look into reconnection event 2. So I introduce some basic concept. Can you guess where in this data we have reconnection? Okay. This is the magnetic field and components, ion speed, electron speed, the magnetic rotational angle, the PVI parameter, which is finding the discontinuities, the current density, the ion spectrum, energy spectrum, the electron energy spectrum, density, temperatures, pressures. First of all, you can see that the pressures are also highly variable. So these are not pressure balance structures in strict sense. Then what we can see that we have these currents here. When we have the currents, then we have this high energy electron ions. Okay. This is the different situation here. We have high energy ions here, but you can see a kind of dispersion that the higher energy ions appear first, and later in time the lower energy ions. So this is probably a remote source which is producing these ions. And locally also we do not have currents here. We have local currents here and non-dispersive ions. I am aware that I cannot explain everything because we looked into this event actually almost 1 year. So the first approximation, how much time I have? 5 minutes, okay. So the first approximation was that we cross a reconnection outflow region, which is resembling the solar wind situation. We cross the reconnection outflow, so we should observe an outflow, and we should observe the discontinuities at the border of outflow, the rotational discontinuities. So the fluid signatures of reconnections are that we try to find a coordinate system in which the electric field is 0. Why? Because in this coordinate system, the magnetic field time variation is 0, so we have magnetic field stationary structures. So there is a stationary magnetic field representing the reconnection, which is there over longer scales, bordered by the discontinuities. So we tested the left hand, by the way, so we zoom into this region, okay, we are here, and we have the rotations in the magnetic field, rotations, changes in the ion speed. So theoretically, it could be an arsenic discontinuity. We tested. This is a arsenic discontinuity. So one side is arsenic, but the other side is not, because the magnetic rotation is too large to produce such a small change in the speed. First. Second, again, we have to look in the scatter plot of the Alfvén speed and the ion speed reduced by the Hofmann-Teller frame speed, which is the speed of the stationary magnetic structure. So we have a reconnection site. It's moving with the Hofmann-Teller speed. And if we have an outflow, we have to check if this outflow theoretically expected to be arsenic, if it is really arsenic. So we have to remove from the observed Alfvén speed the Hofmann-Teller speed. Okay. And if it is showing some correlation, like here, then it is possibly a reconnection site. So this test is okay. But how to interpret these different slopes? To interpret the slopes, we need to establish the element system. So the element system is determined from the application of minimum variance analysis, because along the L and directions we expect different fluctuation power, and also from multi-point timing, because we have 4 spacecraft. So after some time we are able to determine the element system, and this two-dimensional, quasi-two-dimensional reconnection geometry. And you can see again that the electron speed has peaks and the ion speed is much smoother, so we have currents because of the differential motion of these guys. And the question is, if we are, for example, crossing the reconnection along this trajectory, we should observe anti-parallel flows. In the ion speed, we observe here into L direction positive and then negative flows. But it's not enough. Usually in solar wind studies, they are calculating the L directional speed. Why the L directional speed is not enough? Because it's not necessarily the convection speed, or the outflow of the reconnection. It can be also a parallel component, which is a stream and not a convectional flow. Okay, if we calculate the L directional field perpendicular speeds and we compare it with the E cross B convectional motion of the fields, then we can see that the fields, when the fields and the particles are moving with different speeds, we can judge that the ions or the electrons are demagnetized. They are free. They are not moving together with the magnetic field lines. But still, we can have important directions, like the direction of the electric field, the direction of the E cross B direction, and so on and so on. Okay. After some fight, we reconstructed the trajectory. So this is the element system again, and we observe positive and negative outflows. Here, the red is how the field moves, the blue and the black how the particle moves, and we can see that the field here is not moving equally as the particles. So we are moving through the central planetary connection, so the ion diffusion region, and we touch here the electron diffusion region. Moreover, we have a flux slope here, and then again these negative electron outflows. Okay, we can, if somebody is interested, we can speak about it, but you can see when the L perpendicular outflow is 0, we observe an inflow. So from the outflow region, we are going to the inflow region, and then we are going back. Okay. Then, when we are touching this electron diffusion region, there is a parallel electric field, and this parallel electric field is leading to locally enhanced G dot E prime. G dot E prime is the measure for energy dissipation or conversion. If it is positive, then it is dissipation. And then the agyrotropy parameter, which is corresponding to the agyrotropy calculated from the electron pressure tensor, it's also showing a peak. And at the same time, there is a acceleration of electrons to higher energies. So this is a local process, the first place when electrons can be accelerated within the reconnection site, and probably because this agyrotropy parameter in comparison with simulation is relatively small, we are not inside deeply in the electron diffusion region, but we are touching the outer diffusion region. Okay. Here are some examples how the electron VDFs are deformed. This is outside of the electron diffusion region, and you can see that the left and the right compared. Here is the cycle, and here is a deformed distribution. This is temperature anisotropy. This is the agyrotropy, and after some time we realized that the anisotropy is generated by thermal electrons, anisotropy, and the agyrotropy by suprathermal electrons. Here are the typical ion distributions. When we are within the reconnection outflow, we see these D-shaped ion velocity distributions. And these are typically observed in many cases of reconnection outflows. When we are within the ion diffusion region, we have these very complex ion distributions typical for demagnetized ions. Okay. So, conclusions. We observed two reconnection events in the turbulent particle sheets with clear reconnection signatures. The reconnection, on the basis of these signatures, we claim that reconnection in turbulence, at least in these cases, resembles the reconnection at large-scale boundaries, which is fine, because we could learn a lot from those events. However, it's difficult to determine the element coordinate system because turbulence is more 3D. The events can be overlooked even in MMS data. I have some colleagues in grants. They are looking into reconnection events long time. And it took me maybe half a year until I could persuade them that what we see is really reconnection. And the events might not be seen in data sets from previous missions because of the data resolution. Thank you.
So I would like to thank organizers for giving me the possibility to be here and present this talk. So I'm a cosmologist and I'm sorry, a physics person, but I will show that the law of physics are the same everywhere, like in sun, in the galaxies, in the universe as well. So I believe the best view of the turbulence, it is by this Van Gogh turbulent mind captures the turbulence, so the best understanding of the turbulence was presented by the artist. So my talk will be outlined as follows. So I will talk about the cosmic magnetic field origin and discuss the possibility of the primordial turbulence, the turbulence originated in the early universe. I will talk about the magnetohydrodynamic turbulence, including chiral magnetic effect, non-helical inverse transfer, absence of the helical inverse cascade, and I will talk about the classes of the turbulence in general. And by the end of the talk, I will present the results which has been obtained through the runs just a week ago. So it is not published, but we hope to submit the paper soon enough to PRL in 1 week probably. And this will be about kinetic helicity dynamo mechanism. So collaborations are listed here. So it includes the people from completely high energy physics, like Alexey Boyarsky and Oleg Rucharsky, goes from Europe. I also include the people working on dynamo, like Natan Klorin, Igor Rogarchevsky, from the solar physics, Axel Brandenburg, and many others. So it includes also our own Alek Otevzadze, who is here. And also two students, Sayan Mandal and Winston Impos from the Carnegie Mellon University. So when we are talking about turbulence, the first what we feel, so it is just our mind comes to the turbulence when we are flying. So another two examples, it is turbulence in the fluid in the sea, as well as a hurricane, which destroyed, unfortunately, a lot in the US territory last week. So, but the point is that the turbulence exists also in the cosmos. It exists on the sun, exists in the galaxies, in the intercluster medium as well, but and it might be related to the origin of the magnetic fields, and this idea comes from the paper by Enrico Fermi in '49 about the origin of the cosmic radiation. And in fact, the same paper for the first time proposed the idea of the seed magnetic fields in the universe, which results after in the galaxy magnetic fields. So what we know and what we don't know, and so we always know more less than we don't know. So we know the amplitude more or less of the magnetic fields and the cosmic structure. We know more or less the spectral shape, the correlation length, but we don't have any idea where these magnetic fields comes from, where, and what are the initial conditions in the universe. So there are two options. One, it is a cosmological scenarios, and another one is astrophysical scenario. Sometimes they call bottom up and bottom down scenarios. In the astrophysical description, it's assumed the observed magnetic fields came through the astrophysical mechanisms. For example, seeds are generated through the small fluctuation and amplified after through the astrophysical processes. In the cosmological scenarios, it is assumed that magnetic fields were originated in the early universe, and after they involve with the expansion of the universe as well. So here it is a snapshot how the plasma will look like if we do have the primordial origin. So in the beginning, the magnetic field, it's more dense and more high temperature, while when there is an ejection, we have just a very small seeds, and after they are amplified. So if we will be able to make snapshot of the universe in the high redshifts, we will be able to understand what it is, the origin mechanism. Unfortunately, the observations are not so precise yet that we can discriminate between these two scenarios. But what I will talk about, it is even strange, about the primordial turbulence. So when we are saying about the cosmology, about the very early universe, of course we will say, okay, from where this turbulence might come, right? So here it is a brief history of the universe. here it is a formation of the cosmic background radiations from where the photons decoupled from the primordial plasma and propagate almost freely till us. It happens when the universe was like 318,000 years, while today moment it is around 30 billion 800 million years. So it might be that the turbulence exists in the very, very beginning when the universe was younger than 1 second. Even more precisely, I will tell, the possibility of the turbulence comes when the universe was 10 minus 11 seconds old. 10 minus 11, so extremely young universe. And when it can be possible, when the universe goes through the phase transition. What means the phase transition? So when my students asking me, I'm telling him, okay, you're boiling the water, it is a phase transition, right? The same happens in the universe. It's also like boiling there, and there is a phase transition bubbles which collides each other, with the whole of the bubbles moving almost with the speed of the light, and the collisions break the symmetry, and it's produced some kind of probably vortex motion and produce the turbulence. So this is a possibility. Such a stuff can occur during the electroweak phase transition or QCD phase transition. Okay? So now how to describe this primordial turbulence? Don't worry, it is the same, just describe the turbulence in the kitchen when you use open the water and see how the waters flow. The same it is in the galaxy. You just use the same basic laws, nothing else. Now, what is very important for the early universe, such a quantity that the mathematicians call usually Hopf invariant, astrophysicists call magnetic helicity, some particle physicists call chirality. It means when the symmetry is breaking. So we have the matter-antimatter asymmetry, and most probably this asymmetry is related to the parity mirror symmetry breaking in the universe. And when we have the helical magnetic field, here it's like topological nodes where the parity is also broken. So, and of course here's how we define the magnetic helicity as a regular stuff. So, the same stuff like called Carnot magnetic effect, when there is a symmetry between right and left-handed fermions, and first amplification is the external magnetic fields, has been known by the paper of Willingen from 1918. It is completely string theorist person, but it can be applied as a magnetic field generation, and this was realized by Boyarsky and collaborators in 2012, and very recently in August we have published a paper in which we consider turbulent magnetic inverse cascade in the early universe, and I will briefly discuss these results. So it is the snapshots here. So what we will see here in the spectrum of the energy spectrum, we see the saturation of the cascade. We have here K-2 spectrum, not like Kolmogorov kind of K-5 third. And here it is a dumping. So these snapshots of numerical simulations with 3D compressible, very high resolution, 2304 cube. And in fact, such a runs takes like is a supercluster around 1 day, 24 hours, using 96,000 processors simultaneously. So the simulations was done based by the pencil code, which was, on my knowledge, first developed for the solar physics. But we can just change the initial conditions, you will get the possibility to model the turbulence in the early universe. So here it is the first paper in 2010 of the numerical simulation. So we consider two different cases. One was a magnetically dominant and kinetically dominant case. And here you see leftover peak once the energy density has been injected. And very soon the field got some kind of the structure. And very interestingly, independently how was the initial conditions, with the magnetic field you always ending up by the Batchelor spectrum, while the velocity fields allow the white noise. So here it is what I just made in the comment previously. So we injected the magnetic field at 1K mod, so it is a monochromatic. Okay, the monochromatic spectrum, and it starts to be distributed very soon. So here it is a movie. I can show you how this numerical simulation shows. So initially the amplitude is decaying, the correlation length is increasing, and we ending up with almost homogeneous magnetic field correlated on the very large scales. So I go further. The very interesting effect was found out that due to redistribution in the partially helical fields, you are getting the fully helical case in quite short time. So it was also studied by Alek Otorzadze, Axel Brandenburg, and myself in 2012. We studied also when the field that was generated during very early epoch, like inflation one, and we see that this kind of the field has a K-1 spectrum. Here it is when it starts to interact with the plasma, goes to K-5 thirds, as Kolmogorov has been predicted. We have shown that in this case, if the field is completely helical, you don't have any more inverse transfer with inverse cascade, which is a very interesting result, because you don't have any more the room where to push the power on the large scales. And we found in 2015 that you do have non-helical inverse transfers on the large scales, because the velocity fields, which is a generated magnetic field, starts to feed the magnetic field at the large scales, and the power is increasing. So I just give the very snapshot. So we have described the classes of the magnetohydrodynamics turbulence and made the connections with the invariant. We shown that Lutyansky invariant is conserved only for the hydro case, while for the fully helical case you have just conservation of the helicity. But for the non-helical case, when it is magnetically dominant, when there is a possible conservation of this strange quantity, which we cannot explain yet. So we're trying to understand this one through the machine learning. And since I really don't have the time here, I just show just last two slides in which I show the dynamo effect in the decaying helical turbulence. This is something which is in preparation, will be posted online in 1 week, hopefully. And we go to the PRL. So we started with initial, it's kinetically dominant case. The magnetic field is a much slower amplitude. And what you will have, that you get K4 spectrum for the magnetic field, even you started with the K4 by the velocity field, you are getting to the K2, and you are getting like dynamo case in the decaying turbulence, which is a completely strange. So here it is some kind of the numerical data, and here are the conclusion that primordial magnetic hydrodynamic turbulence is a plausible option to explain origin of the cosmic magnetic fields, including the magnetic fields in Sun. So investigation of the decaying turbulence in the early universe reveals some unexpected feature, and this unexpected feature can be applied to the solar wind, for example, and it includes chiral magnetic effect cascade, non-helical inverse transfer, absence of the helical inverse cascade in some case, dynamo effects for helical kinetic turbulence, and we can show that always the magnetic fields end up with a Batchelor spectrum independently of the initial condition, while the velocity field establishes the white noise spectrum. And here it is my thanks. First, I would like thank all of you for your attention, and especially I also want to thank organizers, Timur Zakharashvili, especially, and I would like thanks my collaborators, because it was a very long list, but with Axel and Aleko, there was like many papers written already together, and of course I would like to thank both students working with me on these projects. So thank you very much.
First of all, I would like to thank organizers of the conference for inviting me, for giving the possibility to present our recent results. Actually, this work is still in progress, and I would like to show you some kind of preliminary first part of the results what we have so far. And the talk concerns mainly description of the some kind of analytical polytropic model of flow patterns, what we are trying to develop. I am representing the Institute of Space Research of Austrian Academy of Science in Graz, and also this work has been developed in collaboration with Ilya State University, Avestomani Observatory, Catholic University of Leuven. Also, I have collaborators, Valentin Bernik from Institute of Radio Astronomy, and Horst Fichtner from University of Bochum. This work was, let's say, developed under the projects of Austrian Science Foundation, Schotter-Rustaveli, the Georgian National Science Foundation, and also this is the SolSpanet project, which is already finished, but many of these ideas has been inspired by the investigations we had then. This is the outline of the talk. First of all, I will make some introduction into the motivation, why we want to study at all this issue. Then I will try to have some description why we address the patterns at all, and what type of patterns can exist in the observations or in simulations we have seen during this week as well, a lot of them around. Then we will focus especially out of all these possible types in the large scale flow patterns and solar wind patterns. There will be some formulation and physical content of integration constants. Then we will show some illustrative example of the solution, or what we can build out of this formalism. But before that, we will show some equation which governs the shape of the profiles, velocity profiles, density profiles, and temperature profiles for such patterns. Then we will also briefly mention only the second part. As I mentioned, this work is still in progress, so the second part will be only briefly described when we have the case of adiabatic index not equal to 5/3, and I will make some implications to the partially ionized plasma applications of these solutions. So let us start from the motivations, why we want to study such profiles, and even more try to develop some analytical solutions for such profiles. Of course, we know the flow patterns, even small scale or large scale in the solar atmosphere, they are very complex, and it's quite difficult to model them analytically at full extent, and that's why numerical techniques are used. But still, in some cases, it is possible to have some kind of simplified models where you can gather information about the physics behind the process. And first motivation, what we have some while ago, it has been shown that the waves, the waves which are propagating through the shear flows, and if in this system we have some dissipation processes like viscosity or resistivity or whatever, then this kind of propagation process is able to produce some portion of heat. And this result has been published a while ago, and it is concerning of single harmonic of MHD wave or some set of harmonics. But still, it is needed. There is a need to estimate what is the overall contribution of such process in entire corona or the solar wind. And to do this, we need very specifically defined flow profiles there to have information about the shear rates, because all this energy is taken from the shearing of the flows what are in the solar atmosphere. Another motivation is related to the solar wind modeling itself, and we have seen this morning also very thorough description about the challenges what are in the numerical modeling of the solar wind, and what is the need that we have need to have some theoretical models also to couple the source regions and the regions where this so regions close to the sun, how they couple with the inner heliosphere, and in a sense how to combine this numerical modeling together with the observational data we have here. And for this we focus mainly now to this source region for the solar wind, and we try to model it. So this is the basic motivation, and this kind of modeling, we know they are crucial for the forecasting of the solar space weather events, and also we have kind of framework why, as I mentioned, why we consider patterns, because patterns are carrying some kind of metadata about the processes, and this kind of metadata in terms of kind of artificial intelligence approaches play a role of features, and these features help to develop some models of recognition in the observational data and even in the numerically obtained data, such patterns, and then fine-tune them and make some regression models, etc. So this is the motivation. Now let's move to the topic that Eugene Parker was the first who realized that the solar wind acceleration process has direct analogy actually with the rocket nozzle engines, where we have such equation which and the form of this equation is the same for these two processes actually. Difference is of course in the denominator here, because in this case we have here the derivative of the cross-section of this nozzle, and it is there is no mouse here. It must be illegal. Doesn't work. So we have subsonic side, the green one, and there is the okay, thank you. Then there is some transonic transition to the supersonic flow, and we have similar critical point for the solar wind. It starts to accelerate in the subsonic, I would say, part, and then there is the critical point where Mach number is 1, and then it is the supersonic part. Of course, there might exist another kind of solution which starts from the supersonic state and goes to the subsonic state, and why we call this state it will be seen later, but one indication of this is that in this critical point, actually both nominators and denominators of this ratio are 0, and that's why we have here the smooth transition of the velocity. And this model of Parker describes well some family of solutions related to radial expansion of the solar wind. However, we think that this class of solutions can be expanded, and we can get some wider class of solutions if we try to have the modeling similar to this what has been done by Summers in 1982. His model was based on the two-fluid approach, and this two-fluid approach resulted in very complicated analytical expressions for different cases, and that's why author decided not to go into the analysis of this, because analysis of that was really hard. And in our case, we tried to condense down the mathematics a little bit into the one-fluid approach, and on cost of this, try to have some more physical content out of this. And so we have this polytropic relation between pressure and the density of the plasma, and what is specific to the our model. We do not consider any external forces here, or some source terms for the generation or transport of the entropy, because so this solution, so we from this equation we get these two governing equations, and here we see that when alpha is 1, this is the case what I showed recently, the Parker's case. This system reduces to the Parker solution, but when alpha is 5/3, for instance, then we can have quite simple analytic solution. From the first equation, we get that this term is just a constant, and this equation is simplified by substitution of this into the equation. We get the algebraic quartic equation, actually, which is solvable. And here we have these integration constants, and integration constant C depends on the mass flow rate and the specific entropy. And actually the boundary conditions which determine the values of this integration constants, and that's why we can build some kind of patterns for different sets of boundary conditions measured by the in situ observations or remote sensing, and also we have some connection with the radio observations that has been done recently by us. So this is example of the solution, so-called no-flow solution. It can exist also here in specific case. This quartic equation has such solution, which implies that the velocity along this pattern everywhere is 0, and we have only the profile of the density and the temperature. Yeah, and besides, here usually in such models we know it is very important the conditions for the existence of the critical point, and such in our case such condition is that this delta delta should be 0. And it is easy to show that if this is 0, then k is always positive. And that's why we easily get that this critical point is where eta is square root of c. So out of this information, we build the final equation which governs the transonic flow patterns, which is the critical point here. So here another integration point, constant d, manages the position of the critical point. And here I show one example of such a solution. Actually, we took this as a reference model, one published by Mann et al. In 1999. Why? Because there was a clearly defined some set of appropriate parameters and boundary conditions, which we took as a reference. And in that case, what we got, this is kind of example of the slowing pattern. Why? Because we took at 1 AU velocity 427 kilometers per second, and in this case, the critical point is at 6.91 solar radii, and here it is the temperature profile, which shows one additional information that here we see that the temperature starts at the starting from solar is pretty high. So here another constant comes into the game. This is the altitude of the source. So where the slow wind starts, this can be higher, and we know it might start on top of the streamer belt and at altitudes of the streamer belt, and that's why this kind of approach allows to model the inner source region using these solutions. And here I just make zoom. Here is plotted temperature depending on the electron plasma frequency, and this is the parameter related to the radio observations of the type 3 bars in decameter in any range, in the frequency range. And what we see here, this is the zoom of that last figure. We see here that our solution does not fit to the observations. These observations are in detail described in the poster downstairs. It is the total 2017. And what we see here, this A is depending on the derivative of the logarithm of the electron density and the source velocity, which is taken normally 0.3 c, which you see is the sound, the velocity of the light. Yeah, and so this way we can conclude here that using the radio observations we can even tune these solutions further to get to the better coincidences with the profiles. Here I just quickly show one example for the fast wave, fast wind. And here we see that when we take the 800 kilometers per second, the critical point is much closer to the sun than in the first case. So this is one example. Of course, this is just an illustration, and it needs very rigorous study of that. And in one word, just for general case of alpha, we can get practically the analogous analytical solution, but I'm not going to speak about this because it is the second part of the work which still can be done. Only implication I will make here is that this can be related with the ionization rate. We know that the gamma adiabatic index depends drastically on the ionization, and exactly it drops down drastically from 0 to 1 and from 99 to 100% of ionization ranges. And for that case, this model can be also useful. These are my conclusions.
Thank you. I would like to thank Timuri for organizing this meeting and the SOC for inviting me to do this review. I have to warn you because actually this is the fifth version of this presentation, because during these days I saw that already many information were given, so I changed it a lot and I added a new thing. So I hope that in the end it will make sense what I will say. So this is the plan of the talk. I will start with the definition of eruptive phenomena. I will say how we can observe the events and the phenomena related to these events at different wavelengths, how eruptions can be triggered, how they can affect the chromosphere and the photosphere, and in the end I will say also something about flare-CME correlation. So we start with some brief definitions of flares. Here you can see different images taken on the flare, which is called the Bastille Day flare, because it occurs the 14th of July. And in this image you can see the ribbons of the flare in the photosphere with the sunspots. And in this image, which is taken at 1600 angstrom, you can see both the ribbons, but also you can see some signatures of the loops which connect the ribbons. And these loops become more and more evident as we go towards UV wavelengths. So, as a definition, we can say that flares are magnetically driven phenomena that can involve all the atmospheric layers and beyond, because they can also involve coronal mass ejections. So, during these events, we can have a violent sudden release of energy of the order of 10 to the 28, 10 to the 32 earth. And this emission of energy can last for some tens of minutes or some hours, and can involve the emission in the full electromagnetic spectrum. Here you can see a plot which reports the emission in different wavelength range as a function of time. And in this plot you can see that there is a phase where we can have a precursor of the flare. There is an impulsive phase where we can have a sudden spike in the emission at different wavelengths, and then there is a gradual phase where we can have emission between subject phase, HMB, and H-alpha. So another important concept concerning flares is that during these events, magnetic energy is converted into particle energy, heat, waves, and electromagnetic radiation and motion. Then the other eruptive events are prominences. We already had a review about the characteristics, the properties of these structures. What we can add now is that the filament activation can be considered a precursor of approaching flare activity. And also that filament eruption can occur outside active regions, and in this case these are often associated with coronal mass ejections. In this figure you can see the representation of some models which try to explain how we can have the eruption of filaments. So here you can see a figure which concerns a model which is based on flux cancellation, also about this phenomenon we had during these days. Here you can see also a figure concerning the theta cutting phenomenon. So the magnetic field lines are cut somehow in the lower layers of the atmosphere. Then here you can see a model concerning the field instability. I will say something more about this. and then again flux cancellation, and also this is a model which is called loss of equilibrium. Then we have coronal mass ejection, so expulsion of mass of the order of 10 to the 14, 10 to the 16 grams, velocity of the order of 10 and 3 km per second, and the energy which is involved with the CO2 events is of the same order of magnitude of most of the flares. And often it is observed that when the mass is ejected from the corona, in the corona there are pigments. Here you can see for a sequence of images showing the occurrence of a coronal mass ejection, so taken by the Lasker-Sifry instrument. And here you can see two snapshots of the relative density of the plasma which is involved in a coronal mass ejection, and this is taken from a simulation of this kind of events. So I described three different phenomena, but actually we can consider a kind of unified model of these eruptive events. And this model is characterized by the presence of a filament here. Of course, you know that this is just a 2D rendering of something which occurs in 3 dimensions. Here you can see the current sheet below the rising filament, and here you see the ribbons which are labeled with different colors in order to indicate that as time goes, we can observe these ribbons which appear to move away one from the other, but we know that this is just an apparent motion. What actually occurs is that particles which are accelerated at the reconnection site precipitate at the beginning in the inner loops and afterwards in the outer loops. And this is an image of a coronal mass ejections which, as you can see, really resembles this model. So in order to show that we really can have events that are very similar to this model. And also the last big flare which occurred some days ago showed these structures which again resemble this model. But then about the observations at the different wavelengths. So I would like to start with the optical range. Again, the image of the Bastille Day flare, where we can see the ribbons in white light. We had a nice talk about ribbons observed in white light. So we can say that at the beginning it was thought that only very energetic flares would give rise to white light emission. But now we know that there are signatures of white ribbons also for flares of C+. And then concerning H-alpha observations, so these are very useful in order to record the filament activation and its rise towards higher levels, to study the ribbons in H-alpha or the kernels when the ribbons are not completely visible. Then we can see just some patches of emissions which are called kernels. During the gradual phase, we can also see post-flare loops in H-alpha, and this means that the loops which were filled by the chromospheric plasma due to the chromospheric evaporation gradually cool, and due to this cooling, then they are visible in the H-alpha line. And another aspect concerning the observation in H-alpha is that we can compare the observations at these wavelengths with models, and this can give some hints on why and how we can observe changes in the light profile of flares. In this image we can see the ribbons in H-alpha. With these blue spots indicate the hard X-ray emission, so the foot points in this wavelength range, and in red we can see the soft X-ray emission, which again you can see is indicating that are loops which are connecting the ribbons. If we observe in the UV and in the UV range, we can have some information on the configuration of the region in the chromosphere and the transition region in corona. We can study the process of plasma evaporation and condensation, information on the post-flare loops, and so information about timing, spatial configuration, correlation with white light and the sharp ribbons. Also hints on the fine structure of the erupting filaments, and these observations are also useful in order to obtain some physical parameters of the plasma involved during these events. Then, concerning observations in the X-ray range, in the soft X-rays we can see impulsive brightening, which is due to thermal emissions, in loops which connect the ribbons, as we saw in the previous image. And concerning hard X-ray sources, sometimes we can see three sources. This is the limb of the sun, one which is high above the soft X-ray loops, and two other sources which are very low. And these are caused by Bremsstrahlung of colliding electrons. They appear at the chromospheric heights, and this is what is expected in the thick target model. Recently, there have been observations of so-called quasi-periodic pulsations in hard X-rays with a period of 10 seconds or minutes. And these are interpreted as due to Sasage mode in the loops, which can alter the magnetic field and so can change the traveling of the particles which are trapped in the loops themselves. Okay, then okay, so here you can see how the hard X-ray sources can be spatially correlated with the ribbons in H alpha or in the UV wavelengths. And concerning the hard X-ray spectrum, we can see that there is a non-thermal shape which is close to a power low. And in particular, in this plot, we can see that there is a soft part which is fitted with a thermal component and the high-energy part with the power low. Concerning the radio range, we have emission which is due to accelerated particles which precipitate the spiraling along the magnetic lines, and in particular in the range between 1 and 100 gigahertz, this radio emission is due to gyration of mutely relativistic electrons in the magnetic field. In this plot, which was delivered by Hudson, we can see the different emission, both in the hard X-ray and the soft X-ray, and also the radio emission during the different phases of the flare. And then we can say also something about emission in the gamma range, because during the most energetic flares, we can observe gamma ray lines in this range of energy, which are emitted by atomic nuclei which are excited by ions. But as I said before, this is observed only during the most energetic flares, and this emission is confined to complex sources. And in this image we can see a negative image of the trace image at 195 angstrom, which shows the flare and the places where we have emission, so that this is indicative of the fact that the foot points at 2.22 MeV, which indicate ion precipitation, and the foot points of the non-thermal continuum emission are produced by precipitating electrons do not always coincide. So, what are the main questions which concern flares? How the energy which has been previously stored in the expressed coronal magnetic field can be released so rapidly, can be transported through the solar atmosphere. We saw that we have emission in different wavelength range at different atmospheric heights. So how can this transport take place, and how the energy is converted in other forms of energy? Again, here you can see a scenario which shows the different phenomena which during these events. So, what is actually needed in order to produce an active event? If you assume you have the right start to get this kind of phenomena. First of all, we need a magnetic field. This magnetic field must be stressed in order we can have electric currents and store magnetic energy. But then we also need a trigger mechanism. Several observations indicate that magnetic reconnection is the main driver of these eruptions. But also several observations show that a threshold in some parameters, I will say some data about, must be reached in order to have these events or some kind of instability. Then the energy is converted, and then we have the effects we saw, so particle acceleration, emission of electromagnetic radiation, plasma motions, and in some cases, so not always, but in some cases, we have coronal mass ejections. So, as I said, we need a magnetic field, and if we assume that initially the magnetic field has a potential configuration, so we can also say this current free, they are not electric currents, then due to phenomena which occur at the photospheric layers, we can have a storage of magnetic energy. This phenomena can be, for instance, emergence of new magnetic flux from the underlying layers, can be horizontal motions which produce shearing of the magnetic field, and both these effects are actually included in a parameter which is called magnetic helicity. So, due to these effects, we have a magnetic helicity increase, an increase of the energy. The magnetic field is not potential anymore. It can be, there are several observations which show that the force-free approximation is a good approximation. So in this case, we have electric currents which flow parallel to the magnetic field lines. But again, this is not enough, because then we need the dissipation. So how this energy is then converted in another form of energy. And there is a study by Grisman and Forbes which indicates that for a rapid release, these currents must be concentrated into small regions. And these regions are recognized as the current sheets, which have sizes which we know are not really observable, but we can have some signatures of the presence of these structures. And another important aspect to take into account is that the build-up of energy on its own does not really guarantee the occurrence of an eruptive event. So then we go to the problem of the triggering. So I said it can be magnetic reconnection, it can be exceeding of a certain threshold, so magnetic gradient or certain value of the shear angle, the height of the flux rope, the amount of accumulated magnetic helicity, generally we can say magnetic field complexity. We also know that several flares are occur in regions where we have delta spots. Another triggering mechanism is due to the sudden emergence of new magnetic flux when we already have expressive magnetic field configuration or magnetic field cancellation, or also some instabilities due to nearby eruptions. So concerning the shear angle, here we can see a map of the magnetic field, so with the continuous line and with the dashed line we have different polarities, while the dotted line indicates the polarity inversion line. And these symbols here, the circles, indicate the regions where the transverse field deviates more than between 70 and 80 degrees from the potential field configuration. So the one which does not have energy which can be used for eruptions. While the field squares here indicate the regions where the deviation was greater than 80 degrees. So Hajar and collaborators noticed that a very energetic flare occurred several hours later at the location of the largest shear. So this is a first hint on what could be a trigger mechanism. Then we have the kink instability. So we have a flux tube which is twisted beyond a certain critical limit, then it kinks. And if the twist is between 2.5 and 2.75 pi, according to the study carried out by these authors, then the system undergoes a rapid expansion and equilibrium is not possible anymore. And here you can see a comparison between observations of the eruption of the filament, so if we start from this configuration and then we erupt this one, and the simulations. Another instability which has been recognized to be important in triggering flares is the torus instability. In this case, it has been demonstrated that if we have a dipole field which is having a current ring, and this dipole field scales with 8 as r to 1.5, where r is the radius of the current ring, then the system undergoes an eruption. And when the flux slope reaches an altitude where this decay index of the magnetic field is of this order, then it can have a rapid acceleration. And in particular, in this image, you can see a magnetogram, and these symbols indicate different values of this decay index in the filament, and this is the situation which has been singled out using force-free field extrapolations, where you can see that initially the filament is at this height, while after a while it starts to rise, and when it arrives to this part, which indicates the critical value of the decay index, it erupts. I also said that another trigger mechanism can be due to instabilities occurring close to the site of the flare. This is a study which concerns an active region with sunspots with different polarities, where 3 different filaments were initially lying. At the beginning, one of the filaments erupted, and after some tens of minutes, the other 2 filaments erupted almost contemporarily. So, a study of the magnetic field configuration and expression of the magnetic field showed that there were 2 null points in this magnetic field, and quickly. And so, in the end, it was shown that this active region had a multiple magnetic field configuration. There was activation and or eruption of 3 filaments. There were brightenings in the sites corresponding to the separated surfaces, and post-flare loops were observed, as I said, almost simultaneously in these arcades. So the interpretation was that this event, and especially the biggest flare, which was of class X17.2, occurred to the kind of domino effect due to the fact that the eruption of the first filament completely destabilized the region, so that the magnetic arcades, which were initially confining the other filaments, started to rise, and this allowed the filament. So, how the eruptions affect the chromosphere? I already said something about chromospheric evaporation. I just made a simple cartoon which showed this phenomenon. So we suppose we have a reconnection site here on the top of the loop. Then we have particles which are accelerated and go through the loop, and they arrive to the chromosphere. Then there are Coulomb collisions with the plasma in the chromosphere, so the temperature increases, and this can give rise to an overpressure, which can have as a consequence the fact that the plasma expands explosively in the loop, and so this plasma goes toward higher levels with the velocity between 300 and 400 km per second, so that the loop is completely filled by this plasma. Then these loops are visible in the soft X-ray and UV, but then they start to cool down, and in this case it is also possible to see some phenomena which are called coronal rain. And in this respect, it is also worthwhile to say that a different scenario was proposed by Fletcher and Hudson, assuming that the energy was transported by Alban waves. So these are observations carried out using the ICE satellite, and the result was that in each foot point it was possible to see at the same time upflows and downflows, so phenomena of evaporation and condensation. So we will not say something about this, but I want to say something about sunquakes, because there are observations which show that when we have a very energetic flares, we can also see ripples in the photosphere. And this is still something which is not completely understood, because if the flare energy is released in the corona, in order to drive an acoustic disturbance in the solar interior, we must take into account that the energy must propagate through 9 pressure scales. And then I also wanted to say something about the changes in the tropospheric magnetic field, which has been observed during and after flares, because I had some discussion during previous days. So there is a study which indicates that there is evidence of longitudinal magnetic field changes in X-class flares, so that these authors concluded that on the basis of on the basic assumptions of flare theories, the photospheric magnetic field does not change, but this needs to be re-examined. And so other studies concerning this effect made by Chen on a certain number of flares, and this study showed that 40% of X-class flares showed sunspot structure changes and enhancement of the photospheric magnetic field and magnetic shear. A lower percentage was observed in flares of lower class. This is another study on a similar subject, so a study on another X-flare, and the authors observed the weakening in the horizontal fields, strengthening in the horizontal fields, and some changes in the penumbra of sunspots. And also here you can see a sequence of images which show that during the flare there was a kind of rotation of the of a sunspot. I think I do not have much time to talk about coronal mass ejections. I just want to go back to the magnetic helicity I was talking about before, to say that there are some studies which concern the evolution of electricity during flares and coronal mass ejections, but at the moment it is not possible to single out a general view, because in some cases the magnetic helicity continues to grow, in others it decreases, in others it changes sign. So this is something that we should also continue. And then we have a statistic here about the correlations between coronal mass ejections and flares. And I just want to stress that the highest percentage concerns flares of major class, and this percentage decrease when we decrease the time distance between the coronal mass ejections and the flare. So these were all the aspects I wanted to indicate. Just to finish this talk, I would like to say that we still have many questions, but with the new generation of ground-based telescopes, we could understand many of these aspects. So, concerning the evolution of the magnetic field, how the continuous emission takes place, how sun quakes can take place, and so on. And something similar I also indicated for the different instruments of the solar orbiter. So, thank you.
And also I would like to thank Francesca for a very nice introduction. So here I would like to talk about from our method, where we follow the dynamic evolution of the active flaring active region prior to flare, and we found two typical pre-flare behavior with our method. And from these two typical pre-flare behavior, we try to estimate the expected flare intensity and the expected flare onset time. So our method is based on the following. From the literature, we know that the most promising observer feature is the inversion line separating two opposite areas in an active region, in a delta type active region. And the most probable sites of flare onset are the regions of high horizontal magnetic gradient in the active regions. Actually, this area is very close to the polarity inversion line. So here we present a new insight into the pre-flare behavior and the evolution of the active regions. Here I would like to show two approaches. The first approach is based on the photospheric quantum transport data catalog, and the second approach is based on the magnetic field extrapolation and numerical stimulation in 3D. So these two studies enable us to follow the evolution of the internal magnetic configuration of the active region in high spatial and the temporal resolution. And besides the localization of the flare-producing areas, the present work also intends to reveal the characteristic temporal variation in this region prior to flare. So our required physical quantity, we call it weighted horizontal magnetic gradient between two subgroups closer to the polarity inversion line. So we identify a study area closer to the polarity inversion line, and we follow the evolution of our proxy. We call it VTGM and shortly, or the longest name is the weighted horizontal magnetic gradient. So the upper part of the proxy is a net flux amount the sum of the fluxes in the considered spots of opposite polarity in the study area, and the lower part of the proxy is a distance between the barycenter of the positive and the barycenter of the negative polarity in the investigated area. So we consider this VTGM quantity as a possibility proxy of the non-potentiality from the photosphere upwards to the different height in the solar atmosphere. So, to demonstrate the method for case studies, some energetic events have been selected to follow the development of the magnetic field gradient and to test the viability of the suggested approach. So here, one typical example. This active region produces one X-class flash, and here is our study area, closer to the polarity inversion line. Actually, that's the delta spot in the whole entire active regions. So, in this area, we follow the evolution of the VTGM proxy and the two components of this proxy. So, we found two typical preferred behavior. One of these of the VTGM. Here we can see, first of all, increase this proxy and has a maximum, and after decrease, and just after happen the flag. And also, we found another typical precursor of the distance. First of all, the distance between the two area body centers decreased and has a minimum distance between the two body center opposite polarity. And after these two body centers start receding from each other, and usually the distance comes back about the same value where the approaching starts and just after happen the flag. And I would like to show another example for a small energetic flag. Our Chinese colleagues observed a reconnection process between the small scale loops in the chromosphere. So we asked their data. Here, this blue vertical line indicates when the reconnection process started. So, and here we can see again the VTGM proxy increase has a maximum decrease, and just after happened the reconnection process. And parallel, the distance, the first of all decrease, has a minimum, and after increase, and just after happened the reconnection process. So it seems that maybe this approaching and the receding motion could be a precursor of the reconnection process. So after, the other question is coming. What does happen in the non-flaring active region where we can see a polarity inversion line? Here, in this case, we cannot find only one case, so we just find that only the two body centers sometimes approaching and sometimes just receding from each other. So we don't find the approaching and the receding motion together. So after we do the analysis, more than 100 flaring active region cases, we usually choose the largest intensity flare what the active region produced. So we found two relationships. The first relationship is between the maximum value of the VTGM. In the upper part, the x-axis shows the maximum value of the VTGM, and the y-axis shows the flare intensity. So we found this logarithmic function between the two proxy values. What does it mean? So this relationship could be given to estimate the intensity of the expected flare from the measured maximum of the VTGM. And parallel, we found other relationship. The time of the approaching in the lower figure shows the x-axis shows the time of the approaching, and the other time interval is from the minimum point until the flare onset. This time interval shows the y-axis. So from this linear relationship, it seems that we can estimate the flare onset time, because if we can see that the distance begins to grow again, then after we can estimate the expected time from this time interval. That's okay, but we know the flare actually occur higher up in the solar atmosphere. That's why we extended our investigation in a 3D, in a lower solar atmosphere. Unfortunately, we cannot measure the three-dimensional magnetic fields directly. So we need mathematical tools which is describe how the magnetic structure would be looks like in 3D. So in mathematical viewpoint, we can choose the potential field, linear force field extrapolation, or nonlinear force field extrapolation. In our study, we choose the potential field and the nonlinear force field extrapolation. The potential field extrapolation provides the first view of the magnetic structure of the active region, but the nonlinear force field extrapolation gives a closest picture of the reality from the magnetic structure of the active region. So we compared the results of the two extrapolations. On the left-hand side, we can see the results of the potential field extrapolation. On the right-hand side, we can see the nonlinear force field extrapolation result. We choose one of the four famous active regions in the last solar cycle. And first of all, we tested just only the photosphere. So here, this vertical line highlighted when the X-cluster happened, and we can see the two typical prefab behavior in the two extrapolation cases. Okay, that's good. So now we go a little bit higher. Now we are at the 500 kilometer level from the photosphere. Here we still can recognize the two typical prefab behavior in the two extrapolation cases. So we are happy a little bit. So now we jump a little bit higher. Now we are at the 2,500 kilometer level. We still can recognize more or less the two typical prefab behavior. So during the analysis, we observe that when we go up in the solar atmosphere, we can see that the shape of the component changes as a function of height in the two extrapolation cases. And we also notice that the starting time of the approaching and the time of the minimum point changes as a function of time. That's why we construct this figure. So here, the x-axis shows the time, and the y-axis shows the height at a different height. So we do the analysis every 45 kilometers. So we found that, so the blue line indicates the results of the potential field, and the red line, red color, indicates the results of the nonlinear force field. These first two lines shows when the approaching starts, and the last two lines shows when reach the minimum point. So, and in this red box, we can see that the approaching starts earlier and reach the minimum point earlier. Why good is for us? Because if the approaching starts earlier and finish earlier, we can estimate much earlier the flare onset time, because we use this time interval for the onset time estimation. Okay, here is the other example. I skip it because I don't have enough time. So, after we tested our method in a purely simulation data, so Churchady and colleagues simulated an artificial active region, and they published in the last year. They don't use any observational data in this simulation, so that is good for us. So now we tested the weighted GM method. Actually, this simulated flaring active region produced two B class and two C class flares. And surprisingly, we can identify the two typical behavior during the simulation data. So, which means that looks like it could be a reliable flight precursors, the weighted GM and the distance. And after we construct the same figures that I showed during the extrapolation cases, and even in the simulation, we find that the approaching starts earlier and reaches the minimum point earlier at a certain height, which means that if we use the lower solar atmosphere data, we can estimate the flare onset time earlier than if we use only the photospheric data. So, because we can prove these two precursors by purely simulation data and observationally, it seems that this VTGM method would be part of a future flat forecast method. And top of it, if we can identify the optimum height in the solar atmosphere, that means that the 3D method is capable of increasing the forecast time. And thank you.
Good afternoon, all of you. Before starting, I would like to thank our organizers who has given me the opportunity to present here. So today I am going to talk about the prominence eruption, giant prominence eruption, which is associated with the fast CME. And this was the prominence eruption which happened on 26 September 2014. And this eruption, why I am saying it's giant, that it was carrying a bundle of flux ropes and it was emerging out with the surface, and partially it falls on the surface of the sun, and the bundle that go beyond the LASCO field of view, that is the C3, that is around the 30 solar radii, and even beyond that it's till go to the Mars. So before starting, I would like to discuss about the activities which are going in the long term as well as in the short term. Short term activities over the surface on the sun, which are actually visible, like the prominences or the filament eruption, or that may be the failed eruption as well, or flares, which we call it. But in the long-term activities, we usually observe the sunspot, but somehow we can say that the filament remains there on the surface of the sun. So I'm not going on that. So now I think I have to proceed with the prominence eruption, because today I'm going to talk about the prominence eruption here. So as we all know that the prominence eruption, prominence is just the extended filament which is viewed from the limb, but if we which is extended in the corona, so it is just a loop, or we can say that it's just an extended filament which we observe. Also, when we talk about the prominence, it is not necessary that every time or with any eruption that CME is associated with that, but in many cases, or it depends how energetic it is, and it is still not found that how they are associated with each other. So now I'm going to switch on the coronal mass ejection, which is which happened due to the reconnection, the model given by Shibata, and coronal mass ejection is the eruption from the solar atmosphere and releasing the huge amount of energy in the interplanetary space. And it consists of generally three-part structure. The bright part of the leading edge is called as the shock front, and before that it is, the inner part is called as the core, and the central part, which is generally empty, is, we call it as the cavity. And when we see the flares, and we can see the H-alpha ribbons from the surface here, and also we can observe the X-ray loop. It depends what type of eruption we are observing. So presently, when we are talking about the CME, so this is just a structure of the CME from where about what I talk. So this is the timeline of my event. The event was observed on 26 September 2014, that is in between 4 to 5 UT, and it is that the event happens on the eastern limb. So in this event we have observed the prominence eruption. So at 4 UT we have observed the prominence eruption on its start, and in the LASCO C2 field of view, we have observed at 428, at 428 we observed the CMA in C2 and 530 in C3, and we have also observed the type 3 radio bus associated with this event, but unfortunately we didn't get any type 2 radio bus. So we can say that the type 3 radio bus, if these are associated, these are very much responsible for the particle acceleration. So I have used the data set in this EUV and UV for the from the SDO, and for the optical I have used the Aries H-alpha data. I have also used for CME study LASCO data as well as the stereo data, just to get how the event occur on the other side, because it is of the far side of the sun. So this is Aries H-alpha telescope. It is a Hood type telescope, and have the objective length of 15 centimeter, with the focal length of 225 centimeter. It has the resolution of 1 arcsecond, and we can set the cadence as per our requirement. So for this particular observation, we have used the 5-second cadence data. So this is the evolution of the prominence in H-alpha. I mean, when this prominence eruption started for UT, but we have projected our telescope at some other sunspot group, so that's why we didn't have the earlier data. I mean, for 410. So when we observed, then the bundle, I mean the prominence is also started. It's already started erupting. So we have observed that the bundle of flux rope, it just emerged out from the surface, and it goes into the interplanetary space. But we observe that partially there is some downfall of the filament on the surface of the sun, and we see that there is the detwisting of the filament, due to which we can see here the thread-like structure, because we can say that there was the flux rope which were twisted like a rope, and they were trying to detwist to be in the stabilized condition. So this evolution we have observed in the H-alpha. So we have made some calculations in H-alpha. We found that the initial velocity of the eruption is 84 kilometers per second. Mean velocity we observed at 250 kilometers per second, and maximum which we found in this event is 530 kilometers. These are not the exact value, that is just the approximate values. We found that when we calculate the mass of this bundle, so we found it at the 4 into 10 to the power 18 kgs, and the average kinetic energy of this eruption we found is 3.84 into 10 to the power 31 volts. So now I am going to show this event in AIA. From here we can observe that at 4:15 we see the brightening here, or we can say that the filament start erupting, and from the SDO we can't see that how these legs are anchored to the surface of the sun, but from this we can only observe that how the filament erupts and how there was detwisting in our line of sight. So I have observed in the 171 as well as in 304. But when we look at the stereo data, from here we can say that these, I mean, there are the two legs. Here we can observe these are the two legs which are anchored to the photosphere, and there was a kink here which we observed, and here this was the mass which erupt out, and here we can see that this one leg get cut off, and this portion at 432, I think, yeah, it's 432, so it just it start erupting from in the interplanetary space, and partially it was falling on the surface. So here are the movies. In one is the SDO and one is the stereo. But stereo cadence is not much good we have. Here we can see that how the filament erupts and how it is coming back to the surface. So now I would like to continue with its associated CME. So we have observed that CME occurred on the eastern limb at the 422 or 24 around, but here I am showing at the 438 image, and this one is the cavity, how the evolution, how the CMEs get evolved, and this one is in the LASCO C2 field of view, and this one is the LASCO C3 field of view. Here we can easily observe that this one is the mass which was ejected out from the surface, and we can see that there is the helicity, and this mass is trying to be in the stable state, or we can say that it is detwisting in the interplanetary space. And this is the height time plot of the CME. We have observed that the position angle of the CME was 85 degrees, and the velocity which we found in the LASCO field of view is the 1469 kilometers per second. We have also observed the type 3 radio burst. In that, here we can see that the type 3 is available, but type 2 was not associated with the event. So with that we can conclude that there was a particle acceleration due to type 3 burst here, and this was the highly energetic event. But this event was not Earth directed, so that was not. So we can say that it didn't affect our Earth as well as our mankind, and it just goes off to the interplanetary space. Now I would like to summarize the thing. We have found the dynamic prominence eruption, which was highly energetic, consisting of the bundle of flux rope which was emerged out in the space, and it was associated with the CME with the speed of 1469 kilometers per second. We have found that the CME height in the LASCO field of LASCO C3 field of view is 30 solar radii. So it was not faded off. So we have also found that the filament escape out from the solar surface and partially falls over that. Also we found the type 3 radio burst was associated with the event, and the prominence eruption computed in the H alpha, we found its speed is around 250 kilometers per second. So I would like to okay.
Well, as we know, the sun has a huge influence on the Earth's atmosphere. The sun and space weather have a large impact on our atmosphere. So along with stellar observations and extragalactic studies, solar studies, and solar system bodies, we had atmospheric studies, long-term story of the history of atmospheric studies in Abbas Kiarmani Observatory, which studied in as early as the 1940s. And here on this picture, this is the observatory from in the sky. Here is the main telescope, the stellar telescopes here, solar telescopes, here, and this is the atmospheric laboratory. Right. So, there was established a laboratory of atmospheric studies by optical methods in the 1950s, and since 1957, it had been almost uninterrupted observations of night glow as well as total ozone content. And the scientists, the head of this laboratory for a long time was Tamara Megarishvili, Luisa Fishkova, one of the leading scientists, and many others. They devoted their lives to the studies, and they gathered the unique data and the unique results of their studies. So now there are atmosphere-ionosphere coupling studies, sporadic layers of ionosphere, atmospheric gravity waves, tidal motions. All this data gives us possibility to study long-term trends in the different parameters of the upper and lower atmosphere. And also we can study cosmic factors both in long-term and interannual variations of different parameters. So, these are the instruments that we use. Some of them are upgraded, like photometers. We have new instruments. Spectrometer, all-sky imager, high-frequency GPS, meteor station, aerosol LiDAR system, and all these instruments. Are installed just lately during the last few years. The ozonometer is the only one which has to be changed. So this is just an example of some of new instruments results, the measurements. What are observations from Agostomani night glow observations? So it is made of these lines. This is a schematic picture of different layers. This is the night glow is made of different lines, like H-alpha, hydrogen line, atomic oxygen, red and green lines, hydroxyl, natrium, sodium, and this picture shows schematically these different layers. Atomic oxygen red line, 630 nanometers, is emitted from a height of about 230 kilometers high in the atmosphere. The green line, 557 and 7 nanometers, is emitted from 85 kilometers high. And then from lower heights are hydroxyl bands and so on. So, I said the solar activity in space weather has a huge impact on all this, and we studied this data with respect to different heliogeophysical conditions. In this presentation, I will talk about just a few results that we got from these observations. Mainly mostly about the interannual distributions of various parameters. And first we took the red line intensity, the interannual distribution of atomic oxygen red line, these are months from January to December, and this is averaged emission value of the red line here, and what will be during solar activity maximum is upper line, and for solar activity minimum we got this lower line here. Well, this already shows the impact of solar activity at different phases, and we have different lines, which is quite common. And but as for the interannual distribution of this maximum and minima, it can be a result of both the space weather impact as well as regional effects. The similar data we took from green line, which is similar picture here. This is total average. The upper line is during solar activity maximum, and lower lines is from minimum phase. So, but if we take into the numbers, well, this impact of solar activity is less when we go down in the atmosphere. So the higher, the stronger this effect, the lower, the less effect we have. Well, on the other hand, the interannual distributions of red and green line are quite different. Well, I will not. We also made calculated long-term trends of these lines, which I will not talk about it on this presentation, but just briefly, I want to comment that when we calculated these long-term trends of this, and we took into account annual and semi-annual variations, as well as solar activity, different indices of solar activities, and geomagnetic activity indices. Then we got the trend appeared to be much more confident than without these indices. So then we go down, and then in the atmosphere, and we considered total ozone content, which is in the stratosphere about 30 kilometers height. And what we got, by the way, the solar activity influence is less than it was for the oxygen lines, but we got a strong influence of geomagnetic activity here. Actually, this is we took from southern star commencements. Well, this black line is the total ozone content. It's averaged, and when we took these data for during southern storm commencements, we got this red line. So the total ozone content intensity dropped during southern storm commencements. Then we go down again in the atmosphere, and we consider cloud covering of the observatory. Clouds are formed at about 10 kilometers high and less below. And all this data, long-term data, gave us possibility to to make this distribution of cloudless days during a year. This is for days with a peak in August. where the temperature of this region is the highest this time. And when we consider these cloudy days during geomagnetic, different levels of geomagnetic activity, we get this lower lines here. And the peak of the maximum of this curve shifted from August to September here and March period here. So it's a kind of feature of our region. So we made the numerical approximation of this data, which is quite good, as this is for total cloud these days, and this is for geomagnetic activity. We took relative numbers of cloud these days and nights for this case. And the correlation of the data are very high. So then we took the similar data for cloudy nights, and the difference is that we have maximum number of cloudy nights in September. For days we had in October, and then for nights shifted to September. This is for all cloudy nights. When we take just during calm periods without geomagnetic activity, then the maximum is in August again. So, well, the cloud covering just believe that galactic cosmic rays affect the cloud formation. They take part in cloud condensation nuclei formation. So, thank you. The galactic cosmic rays also make their contribution into cloud covering. We took the data of galactic cosmic rays from Tbilisi ion zone here, and we also found this data for different levels of geomagnetic activity here. And we found that for high geomagnetic activity, the galactic cosmic rays flux decreases during this period. Well, actually, it is a known phenomenon. It's known as Forbush decrease. When it happens, strong solar activity like coronal mass ejections, then the galactic cosmic rays are decreased during this period. We need some more studies to connect this with cloudiness and cloud covering formation. And finally, this is the conclusion that semi-annual variations of the lower and upper atmosphere and ionosphere parameters can be caused by space weather and cosmic factors. And different interannual distributions of cloudless days and cloudless nights at various geomagnetic activity levels that can be caused by the influence of cosmic factors. And this can affect the climate change as well, global temperature and climate change. So different sensitivity to day and to night cloud covering also may affect the climate change. Thank you.
the cloud data, how you actually then separate the meteorological influence on this measurement, what you do, and actually internal climate variation like ENSO and so on in your data sets, and that then you compare with the geomagnetic data with like AP.
Yes.
What kind of cloud cover is detected? That
yes,
are low clouds, or the whole cloud column, or just the high clouds?
No, there is no difference between low and high clouds. I'll tell you. We took this data from nighttime and daytime observations, just because the night glow observations took place during absolutely clear skies and also luminous skies as well. So there should be no clouds. We didn't have meteorological cloud observations those times. We just took it from night glow observational data. So the observations took place during absolutely clear skies. As for daytime observations, we took it from ozone measurements, which took place during days. So this is how we took this data.
And maybe just one note, I mean, when you're doing such kind of correlation, then you have to be aware, I mean, that you try to eliminate or reduce these other factors which can influence, in that sense, the cloud cover. That's meteorological variability and the internal climate oscillation. Otherwise, this correlation doesn't have to be physical. I think that was the problem with many of the correlation which was made in that with that topic, connecting the clouds and the cosmic rays. Because with just simple correlations, it's sometimes really hard to tell what is actually the cause. If you have multiple things which could be responsible for changes.
Yeah, it's of course
it's a problem.
Yes, but this is what we can retrieve from the data that we have.
So when you showed this red line, the interannual variation, you had maxima in June and also in December. So can you give any explanation for that? Because I would imagine tilt towards the sun. I mean, does any sort of seasonal variations have any effect on that? So I would imagine in the summer, you know, the location pointing towards the sun and the winter pointing away from the sun. I mean, I'm talking about the tilt.
Yes.
So does it not come into play, and can you offer an explanation for that? Most maxima at winter and summer.
You mean this?
Yeah, you get that bit. Yeah, that's right. Okay.
Yes, of course, there is it depends also on orientation of Earth's magnetic field towards interplanetary magnetic field. It also may have a regional, maybe a regional effect. So it also has to be studied.
You have almost 14 years of measurements.
Yes, almost.
Do you see any trend, any secular variation in any of the parameters that may indicate some secular variation?
Secular?
Constant variation.
You mean the trend? There are some trends in redline, which we have found here in redline intensity.
Any other questions? It's time for one question over there.
My question is, did you find any correlation between cloudiness and atmospheric parameters, maybe electron density or total electron density?
So thanks to organizers to actually give me this opportunity. What I'm going to talk about today is to do with electron scale physics. So from what you heard so far, it was mostly ion scale physics. So very briefly, I'm going to outline a typical observation. So here we have types of radio burst. You have frequency as a function of time, and that frequency drifts with time because density is decreasing, and because of emission is a plasma frequency. You basically see decrease of density as you go into interplanetary space. And obviously, if you integrate all the radial flux, this is a radial curve, which coincides nicely with impulsive phase of the flare, and this is a Gauss X-ray flux. And so this is a sort of observation I had in mind when I want to apply all this very nice kinetic physics, which I will try to outline today. So basically, I'm going to talk about mechanisms of radio burst, and as we understand it, it's essentially magnetic reconnection producing an electron beam, which then, in turn, generates lambda waves by bump and Taylor stability. And then there are two possibilities. You can either coalesce forward propagating lambda wave with backwards propagating ion sound wave and get an emission at plasma frequency, or if you have counter propagating lambda waves, by three-way interaction process, you can coalesce the two and produce emissions at the harmonic or to twice the plasma frequency. And this is a good reference to see possible mechanisms. And by and large, the issue of what mechanism generates types of radio bursts is not settled, in my opinion. Although I should say that most widely accepted model is plasma emission. So plasma emits radiation is called plasma emission. But what it really is that, and it was outlined by Ginsburg and Zheleznyakov in 1988, then there are other sets of models, mostly phenomenological type, which do not include full kinetics, but they can treat large AU scales. And then there's small scale models, thousands of bilengths, but they are still based on sort of plasma emission mechanism. So what myself and my group at Queen Mary was trying to advocate is an alternative to that. And let me just briefly outline what's the reason behind it. So first of all, let me tell you what is plasma emission. Basically, you have three-wave interaction process. When you have two waves in plasma, they can resonantly interact, satisfying those beat conditions. And so, for instance, you have forward propagating linear wave, backwards propagating linear wave, and if you satisfy beat conditions, you can generate a transverse electromagnetic radiation. So what's interesting is that plasma emission probability is proportional to the vector product of this linear and transverse wave, which means that you have to have the finite angle between the two. Necessarily, this means that you cannot model plasma emission in one dimensions. You have to have at least two spatial dimensions to allow for non-zero angle. So what we've been trying to do is to find a mechanism that can actually work in 1D. And so we try really hard to find one, and it turns out it's possible. And so basically what it is we call it a tendency to plasma emission, and this is called a non-geotropic electron beam emission. So essentially you consider one field line that connects Sun to Earth, and then you have a decreasing density gradient. And crucially, you inject a beam at non-zero pitch angle, so you have a uniform field and you get some finite angle with respect to the magnetic field, and in these simulations I'm setting 45 degrees just to highlight strength of the effect, but it can be any non-zero angle. So first of all, let me show you results of two simulations what happens in the transfers to the magnetic field phase space. So here on the left you see basically this non-gyrotropic beam, and because of the differences of velocity at the top and on the sides, at 3 different times up to say 2000, so it's 0 and 2000 plasma periods, you see that this globe, which essentially is non-gyrotropic beam, you have a preferred direction to the beam propagation, it becomes isotropic in the perpendicular phase space, and as a result, crucially, if you have the gradient, that will produce electromagnetic radiation by wave refraction, and I'll try to explain that in a second. Contrary, if you have gyrotropic beam, in other words, in the perpendicular phase space, you have a ring distribution, then nothing happens, no emission is generated. So, what I'm going to show here is basically a time distance diagram for transverse electric field component. And basically what you see here is that excitation, so as you inject a beam at non-zero pitch angle on the gradient, you get decreasing density gradient, you basically excite a nearly steady wave packet because time goes and it's not moving anywhere. So individual stripes in these blobs oscillate at roughly a plasma frequency, but on top of that you also have modulation by, so this distance between those blobs correspond to electron cyclotron frequency. So you have beating of two frequencies, plasma frequency and electron cyclotron frequency. And so what I'm going to do next, so first of all you see that you have nearly steady wave packet, you have infinite phase speed, but then because of the density gradient, wave starts to refract. And finally, I don't know if you can see clearly here, it becomes, so the slope would be speed of light. So essentially starting from near the standing wave packet, it becomes an escaping electromagnetic radiation, okay? So in the next figures, I'm going to do a Fourier transform, injection location, mid location of the domain. So this is time, this is distance again, and this is the final right side of the box. And I'm going to show Fourier transforms of those. Now, what you see here, corresponding to the leftmost box, you see excitation of left and right polarized. So these black lines, I hope you can see those, correspond to left and right electromagnetic modes. You see a small wave number, which corresponds to the width of the beam, which is spatially localized. But interestingly, because of the density gradient, because density decreases, you could see this parabola to slide down. So you have this parabola here, and then it slides down, and further down. And what you see is that as a result of this density gradient, because parabola came down, your initially small wave number has increased. So effectively, by wave refraction, you increased your k, and we all know that the phase speed of the wave is what, omega divided by k. If k goes larger, then phase speed decreases. So you started with infinite phase speed, a standing wave packet, and then it went down. So as k increased, it went to the speed of light phase speed, which means that it became an escaping electromagnetic radiation. So, so this is basically the result of study 1, which I wanted to highlight, so that if you inject a non-gyrotropic electron beam on a density gradient by wave refraction alone, you can explain electromagnetic radiation generation. I'm not saying it's solving all the problems, because the time scale for gyrotopization is very small. It's only 2000 plasma periods, but there could be some mechanisms which I'm going to talk about later, which could alleviate the problem. Moving on to the second study briefly, which I'm going to cover, is that when modeling plasma emission, so now I'm talking about plasma emission, the classical Gizmo-Zheleznyakov 1957 type emission, there were a lot of misconceptions and wrong results, which we, my postdoc and myself tried to basically clear the air out in the room. So 3 motivations, basically particle cell simulations will typically consider very dense electron beams for the reasons of numerical, you have to, so basically quasi-linear relaxation timescale is proportional to inverse of the beam to background number density. And typically in observations, beams are very dilute. You get something like 10 to the minus 5. But in simulations, they use 10 to the minus 2, which is really awful. And so these works are not reproducible if you try to simulate them properly. And also, there are some erroneous statements that you need 2 counter-propagating beams in order to get coalescence and produce plasma emission. So just, I'm going to just show one slide which summarizes a lot of work, but here it is. Basically, you have 2 results of 2 runs. Run 1, you have dilute electron beam, and this is a dense electron beam. This is a naughty beam, and this is a good beam. And so what you see here is dispersion relation for electrostatic component, electric field, basically. So this is your Langdon wave, and this is your beam mode. And crucially, you see this negative K appearing by the end of simulation. So that means that if you start, if you consider plasma emission with relatively dilute beam, you basically can produce this effect. In other words, you get Langdon wave, initial Langdon wave, which is excited here, to decay into backwards propagating Langdon wave, which backwards means you generate negative K, basically. So negative K is wave goes backwards. And everything is nice. So you can coalesce your Langdon wave with ion sound and get plasma emission, which would appear in the organic component. If you consider very dense beam, what happens is that you excite a frequency which is further below plasma frequency, and so you have here 0.9. This is 0.9. This is roughly 1, and the only possibility for this to become 0.9 is to be of the order of 0.1. But that's impossible because ion sound, so ion plasma frequency is orders of magnitude smaller. So basically, our explanation for all these misconceptions that happened in plasma emission modeling is that they were considering too strong beam, which was inhibiting electrostatic decay, and as a result, plasma emission was impossible. And there are some groups which actually accept that argument and they use now dilute beams, so that at least there's a group at the University of Pierre Marie Curie at Paris that actually use these sets of parameters and accept the finding. Okay, so finally I'm going to talk about the main part of this, or the main topic I wanted to highlight when it comes to generating radio emission with electron beams in the context of type 3 radio bursts. What this relates to is what is known as a Stulok problem, and that basically says that if you let beams evolve according to quasi-linear plasma theory, they would relax too quickly. In other words, instead of having a nice beam, so you have a pulp plasma, you have a beam, it would relax too quickly to form plateau. You stop growing Langdon waves, so in other words, you have no source for electromagnetic radiation. And so the point is that this process, so basically formation of a plateau which shuts down Langdon wave generation would happen too quickly. And so what we try to do is basically to try to simulate for the first time using full kinetic approach how this problem can be alleviated, how you can propagate electron beam up to distances of 1 AU without it being quasi-linearly relaxed, which observationally is the case. So here I'm going to show results of 3 simulations, sorry, quite a few simulations, I think it's 5 runs bulk together. What it is that I think according to Ryutov's 1959 results, there's a possibility to induce ion density fluctuations, and so this inhomogeneity it is hoped to de-resonate electrons from Langley waves. In other words, electrons will not take away energy basically Langley waves will not take energy from electrons and beam will stay intact. So what I would like you to focus is on the blue line, which corresponds to a uniform case, no inhomogeneity. So you see that there are no electrons being accelerated. And you form a plateau, and there is no Langley wave generation at the final simulation, and so forth. Here, those curves correspond to the situation where you have basically a lot of density cavities of the order of, let's say, a few percent depths. Thank you. So these are being energized. So let me just try to briefly outline the theory behind this. This is based on the build of 96-9 results. So you start with Langley wave dispersion relation, and this is D mode. And when both are equal, so that means that they are in resonance, you can do simple, not Taylor, but binomial expansion of the dispersion relation to find that if density fluctuation level exceeds normal dispersion term of Langley, you basically would de-resonate electron beam from Langley waves, and so if you satisfy this condition, then you would basically stop electron beam falling apart as we observe it. So blue curve again is homogeneous, so you can see this is electrostatic energy, it grows in time, which means that Langley waves are continuously generated up to until the very end. All the other cases which correspond to density cavities, they actually, electrostatic energy goes down, which means that they are stopped, so Langley waves are being stopped being generated, okay? So it does work, it seems to work, and now let me show you dispersion relation dynamics in time for the uniform case. What you see is, as a result of quasi-linear relaxation, you see increase in wave number, and this is because phase speed goes down. In other words, you are joining bulk plasma population, but crucially, you don't see any negative K waves. In other words, there are no backwards propagating Langley waves. And this is basically electrostatic energy, electric field as a function of time for the uniform case. What you see is some sort of form of clamping, but everything goes to the right. There is no other dynamics that go into the right. And this is corresponding energy, which doesn't, E squared, EX squared, basically. So now let me show you results where you have actually a lot of ion cavities in a random manner. Okay, you see usual quasi-linear relaxation, but crucially you see generation of negative K Langley waves, okay? And this is by the wave refraction alone. And why I'm talking about refraction, I'm going to show you in the next slide. Now, this is your ion density. You have this density cavity. So look at this wave packet. It goes to the right, hits the positive density gradient, and then is being refracted, being reflected to the left. And then there is another the next one comes in and is being reflected back. So you do see so this negative K that I've shown you in the previous dispersion relation diagram is being produced by reflection on the positive side of the density gradient. And just to summarize these results, basically you have uniform case, you have dispersion relation produced by quasi-linear relaxation gives you increase in K, but no negative K numbers. On the other hand, when your density fluctuations, well, they're static in time, but let's say of the order of 5%, you generate negative K, and effectively this de-resonates electrons from Langley waves, and effectively energy exchange between Langley waves and electrons is, beam electrons is hampered. Just to really make the point, this is time distance diagram for electric field energy, and as you can see, this reflection is there. So waves reflect back and forth. And these dashed lines indicate cavities, so you can see that on the edges of cavity, the wave packets, linear wave packets are being reflected. Okay, so this is a summary slide. Fortunately, I don't have time, obviously, to go into full physics of it, but I would like to refer to 2014 paper where we have shown that if you inject an electron beam into a positive density gradient, what happens is that it results in a decrease of wave number k, and obviously if k decreases, omega usually stays the same. That means that phase speed of the wave needs to go high, and hence we see particle acceleration. So in other words, Langley waves are resonant with higher velocity electrons, and that is why in the inhomogeneous case we actually see those non-thermal tails on the electron distribution. And so the key point of this third study which I was presenting is that drift towards smaller wave numbers, which were including the negative ones, so we drift towards negative ones. It does not require three-wave interaction. So in this case, ions were kept static, and therefore there is no ion sound in the simulation. So just wave refraction alone can produce backwards propagating Langley waves, which in turn can, by three-wave interactions, produce electromagnetic radiation. And on contrary, negative gradients and normal quasi-linear relaxation, in other words, the plateau formation, both lead to actually increasing k and therefore have no effect on particle acceleration as such. So the bottom line is, or take-home message is that inhomogeneity may indeed detune wave-particle interaction, and so electron beams can continue into interplanetary space unhampered. So thanks for your attention.
So my question is related to density. Was it consistent or was it just given density? I saw three different cases.
Yeah, there were three different cases, yes.
First rule, it was just given fixed, yes?
Well, actually, in the first, yes, they were fixed. You basically specify a decreasing density gradient.
Yeah, and then just keep it like that, yes?
Yeah, just keep it like that, but not artificially. I mean, we kept it in pressure balance, basically.
Okay. And in the third case, was
in the third case,
it's very important because later I go to the...
yeah, so the point with the third case is that, well, because of, well, it was basically, so the ion density profile would dissolve very quickly.
So it was consistent.
No, it was kept artificially. So we kept static ions.
Yeah.
Basically, we want to switch off ion sound as such, and therefore in the code.
Even without ion sound, you must have induced scattering, with three-wave or two-wave interaction with Langley waves as well. You have induced scattering on electrons, that is a nonlinear factor. And you can introduce this phenomenon. So, but important in both things is that density is kept self-consistent.
It's not self-consistent. It's kept static for the reasons for the density profile not to fall apart. Because if your equilibrium falls apart, then you cannot. It will be.
No, but it destabilizes or opposite, stabilizes the situation. So sometimes it's better to have self-consistent because
right.
At some stage you are at stabilization.
We do have plans to relax that restriction and make ions to be movable, but before that we have to resolve the problem, keeping the self-consistent in the profile. Thank you. That's something we're trying to look into, yeah.
Any other question?
Thank you. First of all, I would like to thank the organization for this amazing meeting, this great week in a great city. I will present a part of my PhD in the Center of Radio Astronomy at Astrophysics Mackenzie. with Sergio Spiegel, Guillermo Jiménez de Castro, and from Glasgow University, Alexander Martino. Well, sometimes ions are accelerated during solar flares of energy UV, and such particles arrive at Earth. Measurements of Mayer and recently Richard show that. On the other hand, observation of gamma rays at approximately 100 MeV means that such ions may interact with the solar atmosphere. So protons whose energies exceed 270 MeV in the case of proton-proton collision, or 200 MeV in the case of proton collision, can produce charged and neutral pions. The charge of pions decay in muons in about 10 to 8 seconds, and subsequently positons and electrons in 10 - 6 seconds. These positrons are one of the most relative particles that occur in solar flares. The neutral pions decay charged muons, charged pions decay in charged muons, excuse me. No, the neutron pions decay into gamma directly at 70 MeV. And in a small percentage, neutron pions could decay in a positron, electron, and photon via its decay. The gamma ray emission here on the figure spectra of the flare of 25 August 2001 from Kurt et al. Shows the bumping tail here at approximately 70 MeV that shows that protons are in the solar flares. Otherwise, we cannot explain a gamma ray like this. From last decade, systematic observations of solar flares at terahertz frequencies have been made, for example, by COSMA between 210 and 118 GHz. Nowadays it's inoperative. The Solar's Sublimetric Telescope, it's one of our instruments situated at Los Andes Argentinos, continues observing the Sun with great results at 212 and 405 GHz. And AMA has been started the Sun observations with bands 3 and 6 corresponding to that frequencies. And we expect for the next year the Large American Millimeter Array project from Brazil and Argentina with to start its observations in bands 6 and 9. This will be good for a solar physicist because YAMA will have a great interest in Sun. Because an example here of the terahertz observation is a flare for November 4th, 2004, in which for the first time was observed two different components, the well-known geosync and the sublimetric component. We have 2 points here. The left the time profiles for the microwave and the two of SST. In the right figure, the spectra of the Earth showing two different components. Q1 and Q4 corresponds to the maximum and minimum peak flux at sub-terahertz range and the time profile. So new instruments will be important to file and comprehend better the sublimetric component. So we have these two points. We have experiments doing the solar team with 3 and 7 terahertz. Another optical in 30 terahertz, but we need more points to fill this component. Well, for our simulations, we use the FLUCA, fully integrated Monte Carlo simulations package for interaction and transport of particle and nucleic matter. FLUCA includes biophysics models for nuclear interactions, electromagnetic processes, and fast particle and neutron slowing down and scattering. Also allows to suppress processes and hold particles to analyze separately. Our model consists, it's a simple model, consists of a cube with typical length of magnetic loop divided by a two plane at z equal 0. The top part of the cube represents the chromosphere plus the photosphere with hydrogen, helium, carbon, nitrogen, and oxygen with astronaut densities and densities to obtain the thick target model. The at column depth to stop all the particles. The bottom part is the corona, so Fluke treats the very low densities as a vacuum. The primary beam here is related from the corona to the density atmosphere. And on the second, the Fluke calculates all the Bremsstrahlung process, the electromagnetic process and all that. And then we have here some scoring, and we get all the secondary particles generated from, for example, positons and electrons, and photons, pions, muons, etc. The rest with the particles which don't cross from the atmosphere to the corona, we will take into account. Well, we have some control of the beam, so we can use protons, alpha particles, or heavy ions with an angular distribution. We use beam it, model beam it, with tropic downward or pancake, and power law as the energy distribution. Here an example of energy distribution obtained with Fluke. Here we have always shown that kind of graphics will be the photons, positons, and electrons. In the photons we can see the manipulation line, the capital line, and here the first one, 0.0. So we use the proton beam with energy from 0.2 to 1 GeV. In this case, in spectral index 3 for different angular distribution. And as we can see, the shape of the curve is similar except for the knock-on electrons. Because the electrons, we can clearly difference something different here. Electrons knock-on are electrons produced by ionization by atoms in the dense atmosphere to the collisions from accelerated ions. And as an example, in this case, the maximum energy that these electrons can win is 3.3 MeV. So we can see clearly here at more or less 3 MeV that these electrons falls down, and this other part of electrons are from ion decay. So the interesting thing is that, for example, for a proton beam collimated or isotropic or pancake, there is 2 orders of magnitude. All these results are normalized per proton. Well, here are the energy deposition of electrons due to different angular distributions. Here we have the x and y, x and z plane, the x, z, and x, y for protons, collimated protons, and isotropically. As we can see, well, this is a big target for protons, of course, it's a big target for electrons too. And it's interesting that I say the protons isotropic, more electrons cross the corona, and it will be trapped at the loop, and will be emitted radius. Other tests for different spectral index, we're taking different normalizations, but similar shapes. For a soft spectral index, nuclear limitation to fewer photons per beam appears. Here, for example, the soft and the delta equal to 5, the red line, you can see 5, 4, and 3, the carbon line. The other, the shape are very different, but from the softer to the harder, there is at least 1 order of magnitude. For the same distribution, in this case, we analyze separately the pi contribution as an exercise, for example, with Fluke. In the ray spectrum, we can see here that the pi of 0 is the response for that bumping tail. For the positrons, in this case, the main part of positrons we expected is from the pion minus. But here we expect these are the violet ones are the knock-on electrons, as we say, that falls down at 3.3 MeV, more or less. And then we have the red from the pion minus, and 2 contributions, not unexpected, but because the proton-proton produces more positive particles, there is a contribution in for electrons, secondary electrons, of pion 0 from Dalitz decay and from pion plus from Baba's country. So once we obtain the energetic distribution of secondaries, we calculate the synchrotron radiation to this particle to get the fluxes in FU. So Fluke follows each primary particle and all generated from primaries to calculate the transport and the interactions with the matter. So if we turn the magnetic field, Fluke calculates the explicit integration of the Lorentz force equation. So due to this disparity between the system length scales and the particles already, the computer time to do these calculations is practical. So during this PhD, our main goal is to try to make the guiding center description to more practical approach. So meanwhile, we calculate the synchrotron radiation flux to the secondaries using the Rho-Matic code. And we modify, because the Rho-Matic code is for a power law energy distribution, we modify that lecture because we want to read the distributions of Fluke, which are not the power law. This is just an example from this emission. Show flux density of synchrotron radiation due to an isotropic number proton with energy from 0.2 to 1 GeV, delta equal 3, and for the Rho-Matic code we use a magnetic field of 1000 Gauss, 1 to 31 protons, V1 of 45, and the source size here for a 1 arc second and for 20 arc seconds. Knock-on electrons became important at microwave frequencies. Here they dominate the microwave frequencies in both cases, and positrons dominate, for example, on the submillimetric frequencies. Finally, I show you a RASI observation for the solar flare from 23 July of 2002. As Francesca mentioned, the red zone here is for the Soft-Series ray, and here we can see the hard-Series ray and the points. And minutes later appears in a different location the 2.2 MeV gamma ray emission. The gamma ray emission is a neutron capture line, which implies accelerated protons. So this is interesting for us because nowadays we don't have a special resolution in sub-terahertz, submillimetrical instruments, to distinguish the emission from the primary electrons and from the secondary particles. But new observations, for example, for ALMA or YAMA, could constrain the location where ions are accelerated and give us clues on how these ions are accelerated when compared with the models. And well, the conclusions and prospects. So the secondary electrons cannot be negligible nowadays, we think, because depending on the angular distribution, could be more times electrons than positrons. Electrons dominate in the microwave range, positrons dominate the sub-terahertz range, and the shape on the spectrum could give us clues about the mechanism of ion acceleration in solar flares, as for example, the angular or energy distribution. And so prospects of future works will introduce a magnetic field in our model to obtain more energy distributions. Try to respond how important are the secondary electrons for the theory. Can we constrain the rotation of accelerated particles with ALMA or YAMA? And for example, calculate other situations as acceleration, primary particles trapped on a